Hi everyone, in AI art generation course. Did you ask yourself previously how artificial intelligence is able to generate all these amazing images? The answer is stable diffusion models. In this course, we will learn how these models work and how can we use them to generate amazing images. We will learn how to use stable diffusion models to add a new style to our own images. And we will learn also how to upscale our images, how to increase the resolution of our image by using a stable diffusion model. And we will learn how to do face restoration. And we will learn how to divide our image that we want to generate into regions and how to put what we want inside each region. We will also train our stable diffusion model on our personal images to make it able to generate our faces but with different styles. And we will learn how to talk to our stable diffusion model to generate these amazing images. We will also talk about inpainting, and we will learn how to change a specific region in our image. In other words, how to regenerate this region to get what we want. We will also learn how to change the style of the haircuts in our generated image without affecting on the other regions. And we will also learn how to specify the background that we want using stable diffusion models. And finally, we will learn how to convert our video into animation. Here is our original video, as you can see here. And here is the animation video. So what are you waiting for? Join us. Hi everyone. In this course we will talk about stable diffusion model, and we will learn how to create these amazing images using artificial intelligence. Firstly, what is stable diffusion model? It is just a machine that converts any text into amazing images. As you can see here, we have this text, oil painting Naruto robot. We will pass this text through our machine, which is our stable diffusion model, and our stable diffusion model will create this amazing image. This image will have the characteristics of the robot and Naruto. That's amazing, right? In this course, we will learn how to implement this machine and how can we train it to create these amazing images. But before talking about how to create them from scratch and how to train them, let's use a pre-trained stable diffusion model, which is a model that trained previously on very large number of images. Here we will use Colab notebook to write and run our code. So if you have a Gmail account, you can open Colab easily. We will press on this link here, and here we will click on new notebook like this. So now we have this notebook, Colab notebook. Here in this course we will use diffusers library, which makes it easy for us to work with the stable diffusion model. So firstly we need to download this library and all its requirements. To do that we will use this pip command. This command will download any package that we want. So we will write pip install, and here we should write the name of the packages that we want. So here we will download diffusers package, datasets package, transformers package, accelerate package, FTFY package, and finally Pyro version 9.0.0. We will use all these packages through our course. So now let's run this cell to download all these packages. We just need to click on this symbol here. Now all the packages have been downloaded. To create a new cell, you should go in this place here and click on this place here. You will get this new cell and you can write your code in this cell. Now, as we said previously, diffusers package makes it easy for us to use any pre-trained stable diffusion model to generate artificial images. To do that, we should import diffusers package. So we will type import, and here we will type diffusers package. Okay, and we will click here. Now that we have imported diffusers package, we can use it in any cell. Let's use it in this cell here. As we said previously, here we need to use a pre-trained stable diffusion model, and we want to generate artificial images from it. So firstly, we need to download this pre-trained model. Actually, there are many pre-trained stable diffusion models in Hugging Face community. We will take this pre-trained model. We will copy the checkpoint of this model. To do that, we should click on this place here. Okay. Now, from diffusers package, we will import stable diffusion pipeline like this. Okay, we will use this stable diffusion pipeline to download our pre-trained stable diffusion model and use it to generate images. Now we will create this variable, model ID variable, which is equal to the path or the name of our pre-trained stable diffusion model that we copied previously, which is this ID here. Okay, so we will put it here. So now model ID will be equal to the checkpoint name. We will pass this ID to stable diffusion pipeline so that we can download this pre-trained stable diffusion model. So now we will create another variable, which is model variable. This variable will be equal to stable diffusion pipeline dot from pre-trained. We will use from pre-trained method to download our pre-trained stable diffusion model from Hugging Face community like this, and here we will pass model ID. And we can also change the precision of our model. Here we reduced the precision to float 16. By doing this, we will speed up our model. We will talk about this in depth in later lectures. And now what we will do actually, we will send this model to our GPU. Colab Notebook will give you free GPU. When you send your model, your stable diffusion model to GPU, by doing this, your stable diffusion model will be very fast. In other words, it will create the images quickly. How can we do that? We will type dot 2, and here you will pass the device that you want to put your model in, which is coda. Okay, coda 0. This is the name of our GPU. And here actually we also need to import torch. Import torch. Stable diffusion pipeline will use this library internally to create our stable diffusion model. We will use this torch package through this course. We will talk about it in depth in later lectures. Okay, so let's run this. Okay, now we will download our pre-trained stable diffusion model from Hugging Face community. Actually, it will take some time to do this. Let's see the error message here. He said that no CODA GPUs are available. So here we should change the runtime of our Colab notebook. How can we do that? We should click on this place here, and we should click on change runtime type. We should click in this place and click on GPU. Okay, after that we will click on save. Now we should run all these cells again and see if it will work or not. It works fine. Now let's create artificial images using stable diffusion model. Firstly, we need to write the text that we want to create our image based on. So we will type text, and here we will write the text. So let's say oil painting Naruto, like this. And now we will create our image based on this text. So we will type model, which is our stable diffusion model, and we will pass the text, this text here. And there are many other parameters that we will talk about them in details during the course. The first one is number inference steps. We can make it any number, let's say 200. And the second one is guidance scale. Let's say it is equal to 7.5. During the course, we will talk about each one of these parameters and how to find the value for each one of them. So now you don't need to worry about them. And finally, we will type .images like this, and our stable diffusion model will create an image based on this text, and we will put it in this image variable. So now we will run this cell and see the result. This image was generated completely using artificial intelligence, and you will not find it on the internet. So now, if you are interested in stable diffusion models, come and join us. Hi, in this lecture we will talk about Gaussian distribution. Here we have two axes in this distribution. Here, this y-axis will represent the probability density for each value in x-axis. The area under this distribution will equal to 1, which means the probability of getting any value from this range will be equal to 100%. In other words, it is impossible to get a value from another range. So here, the area under the curve represents the probability of any specific range of values. And we can say that the probability of this range, it is greater than the probability of this range of values, because the area under the curve here, it is larger than this range here. And by probability I mean the chance that a value will be selected from a given range. So now, why we need to use this Gaussian distribution? We need to use this Gaussian distribution to take random values from x-axis based on the probability density on y-axis. And why we need to do that? Because we need to add a noise to our original information. Let's say that we have this pipe number and we want to add a noise to it. So we will get random value based on our Gaussian distribution, like +2, and we will add it to our original information, which is 5, so we will get 7. Now we added this noise to our original information. You should know that it is important to learn how to add a noise in stable diffusion models. Now you should know that there is a special case of Gaussian distribution, which is standard Gaussian distribution, or we call it normal distribution. In this distribution, the standard deviation of this distribution will be equal to 1, while the mean equal to 0. Firstly, let's talk about this standard deviation. This thing here will control the width of our Gaussian distribution. When we reduce the value of this parameter, the width of our distribution, our Gaussian distribution, will reduce, while when we increase the value of this parameter, the width of our Gaussian distribution will increase. And the mean here, we will use it to shift our distribution based on our original data. As you know, we will add the noise on our original data. And this normal distribution will not have any data, so the value of this mean will be equal to 0. Now, let's say that we have very simple image which has 4 pixels. Okay, the value of pixel 0, it is equal to I0, the value of pixel 1, it is equal to I1, the value of pixel 2, it is I2, and the value of pixel 3, it is I3. Now we will learn how to add a Gaussian noise to each one of these pixels. We will multiply our original information, let's say I0 here, with the square root of 1 minus the standard deviation squared. Or we can also call it the variance. A plus n0, which is a noise that we took from the standard normal distribution, where the standard deviation equal to 1 and the mean equal to 0, times the standard deviation. So here, why we multiplied our noise that we took from our normal distribution with the standard deviation. Here, this is standard deviation. It is not equal to 1. It is something different. It will control the amount of noise that we will add to our original information, which is I0 in this case. So, when we increase the standard deviation, actually its value should be between 0 and 1. When we increase the value of this standard deviation, so in this case, the value of n0 times the standard deviation will be larger. So we will add large noise to our I0, to our original information. But what is this term here? The square root of 1 minus the variance, or the standard deviation squared. When we increase the standard deviation, which means we will increase the variance, in this case we will reduce the value of this term. So in this case, I0 times the square root of 1 minus the variance will be smaller. So when we increase the noise, we will reduce the value of the original information. So why we need to do that? The idea behind this term here is when we want to increase the level of our noise, when we want to increase the amount of our noise, we should reduce the value of our original information. By doing this, if we want to convert the value in our pixel into just some noise, we can remove our original information by making the standard deviation something closer to 1. So the square root of 1 minus the variance will be something close to 0. When we multiply this thing with our original information, the result will be something close to 0, which means that we removed most of our original information and replaced it with noise. And if we want to reduce the value of the noise, so we need to reduce the value of the standard deviation. And if we make the value of the standard deviation something closer to 0, so at this case, the square root of 1 minus the variance will be close to 1. So we will multiply our original information with something very close to 1. At this case, we will lose very small amount of our original information, and we will replace them with a small amount of noise. The same thing we will apply with the other pixels, okay, in our image, our simple image. So now we learned how to add a noise to our original image. Thanks for watching. Hi, in this lecture we will answer this question. How does a stable diffusion model work? Let's say that we have this clear image, and now we will add a noise to each pixel in this image. So we will get noisy image 1. Let's now add another noise to each pixel in our noisy image 1. So we will get noisy image 2. So now our stable diffusion model will try to reverse this process. So it will try to figure out what is noise 2, and we will remove this noise from our noisy image 2, and we will get noisy image 1, and our stable diffusion model will try to predict noise 1. After that, we will remove this noise 1 from our noisy image 1 to get our clear image again. So in easy words, our stable diffusion model will try to remove the noise from our image. Hi, in this video we'll talk about Markov chain. Let's say that we have clear image, and let's call it x0, which is our image at time step 0. And now we will add a Gaussian noise to each pixel in our image. So we will get x1, and now we are at time step 1. And here this output x1, it is not constant, because the noise that we will add to each pixel in our x0, we will take it randomly from our Gaussian distribution. So here we will get a distribution for all possible values for this x1 variable, or in other words, a distribution for all possible noisy images that we can get after adding Gaussian noise to x0. Each possible noisy image will have probability density in this probability distribution. Unlike what we said in Gaussian distribution, here the range of values with large area will have high probability to be selected. And this probability distribution will just depend on x0. So when we change the value of x0, this distribution will change also. Or in other words, this distribution will depend on the previous time step only. And that is the idea behind Markov chain. The next step will just depend on the previous step. We will call this distribution a Q distribution. And this distribution, as we said previously, will just depend on x0. So we will call it q of x1 given x0, which means the probability distribution of x1 variable given the value of x0 variable. And as we said previously, we will use this distribution to get the value of x1 variable. And now we have x1 and we are at time step 1. We will add another Gaussian noise to each pixel in our x1 image. And we will get x2 image. And now we are at time step 2. And this x2 image, we will take it from this distribution. And this distribution will just depend on the previous variable, which is x1. So by knowing the value of x1, we will be able to create this distribution that we will use to get the value of x2 variable. And we will call this distribution q of x2 given x1, which means the probability distribution of x2 by knowing the value of x1 variable. We will use this distribution to get the value of x2 variable. The range of x2 values with large area in this distribution will have high probability to be selected when we want to pick x2 value from this distribution. We will do the same thing again and again until time step t capital. So, in simple words, Markov chain means that the next step will just depend on the previous step. Hi, in this lecture we will talk about forward diffusion. Let's say that we have clear image x0 at time step 0, and here we will add Gaussian noise to this image, and we will get this Gaussian distribution. The mean of this Gaussian distribution will be equal to x0 times the square root of 1 minus the variance. And the variance here, it is the variance of the noise, of the Gaussian noise that we added to x0. And we will use this distribution to get the value of x1 variable at time step 1. And we can represent this distribution by q of x1 given x0. Now let's say that we took the value of x1 variable from this distribution. Now we will add Gaussian noise to this value and we will get this distribution here. The mean of this distribution will be equal to x1 times 1 minus the variance of the noise that we added to x1. We will use this distribution to get the value of x2 variable at time step 2. We will represent this distribution by q of x2 given x1. And we will do the same thing again and again until time step t capital. So in general, q of xt given xt minus 1, it is equal to this Gaussian distribution that we will use to get the value of xt variable, where the mean of this distribution is xt minus 1 times the square root of 1 minus the variance at time step t. And here is the variance of this Gaussian distribution. This symbol here, it is just another way to represent any Gaussian distribution. And there are many other ways. Here in this way, we just need to put the name of the variable and the mean and the variance of this Gaussian distribution. So now, this distribution q of x1 given x0, it is equal to the Gaussian distribution that we will use to get the value of x1 variable, where the mean of this distribution will be equal to the square root of 1 minus the variance at time step 1 times x0. And here we will put the variance of this Gaussian distribution, which is the variance at time step 1. The value of the variance will specify the amount of the noise that we will add to x0. And this I capital here tell us that we will apply the same variance for each pixel in our image. As you know, each variable here represents an image. We talked about this previously in Gaussian distribution lecture. Here is the most important thing. Let's say that we want to find the distribution of all possible sequences of x1 and x2 variables given x0. We call this distribution joint distribution, and this distribution will describe multiple variables. Here in this case, two variables, x1 and x2. This distribution will have the probability density for each possible combination of x1 and x2 variables, or in other words, all possible sequences of x1 and x2. It is equal to the distribution of x1 variable given x0, which is q of x1 given x0, times the distribution of x2 variable given x1. So q of x2 given x1. This is forward diffusion. So now, forward diffusion, it means finding the joint distribution for all the variables from x1 to xt capital given x0. Or in other words, in forward diffusion, we are trying to find the distribution that will give us all possible sequences from x1 to xt capital given x0. And we can use this pi symbol to represent this multiplication process. So here we will write pi from time step 1 to 2 of q of xt given xt minus 1, which is equal to this multiplication here. In general, if we want to find the joint distribution of x1 to xt capital, we just need to multiply all the intermediate conditional distributions of each xt given xt minus 1. Let's say that we want the joint distribution for all the variables from x1 to x10 given x0. Or in other words, the joint distribution for all variables in the first 10 time steps given x0. So here we need to multiply 10 distributions together to get this distribution, which is something difficult. So we need to find another way to solve this problem, to move us directly from x0 to any time step and avoid using this joint distribution. Actually, what we really need is to find the value of xt directly, in this case x10. Here we can extract x10 from this joint distribution, but this thing will be difficult. Actually, it is computationally expensive, and we need to do integration to remove all the other variables from x1 to xt minus 1. Here in this case, we need to apply 9 integrals to remove the variables from x1 to x9. By doing this, we will be able to find the distribution that we will use to get the value of x10 variable given x0. So in other words, when we increase the number of time steps, things will become more difficult. In the next lecture, we will talk about reparameterization trick that we will use to solve this problem and finding q of x10 given x0 directly. Hi, in this lecture we will talk about reparameterization trick. Previously, we said that if we want to find the joint distribution for all variables from x1 to xt capital, in this case x10, so we need to multiply the distribution of x1 variable given x0 and the distribution of x2 variable given x1 and the distribution of x3 variable given x2, and we will do the same thing again and again until the distribution of x10 variable given x9. So now the question is how to avoid multiplying the distributions, or in other words, we need to avoid finding the joint distribution and use another way to find q of x10 given x0, because as we said previously, using the joint distribution to find q of x10 given x0, it is something difficult. So reparameterization trick will solve this problem. Firstly, you should know that we will use this symbol here to represent the noise that we will pick from the standard Gaussian distribution, where here epsilon 0, it means the noise that we took from the standard Gaussian distribution at time step 0. Epsilon 1, it means the noise that we took from the standard Gaussian distribution at time step 1, etc. As we said in the previous lectures, the mean of the standard Gaussian distribution is 0 and the variance is 1. And we put it I capital here to say that we will pick a noise from the standard Gaussian distribution to each pixel in our variable. And here, let's say that alpha t symbol, it is equal to 1 minus the variance at time step t. So now, xt, this variable, it is equal to the Gaussian distribution, where the mean, it is equal to the square root of 1 minus the variance at time step t times xt minus 1. And the variance of this distribution, this Gaussian distribution, it is the variance of the noise at time step t times I capital, which means we will use this distribution for all pixels of our variable xt. And we can write this Gaussian distribution this way that we used previously, which is xt minus 1 times the square root of 1 minus the variance at time step t plus the standard deviation at time step t times epsilon t, which represents random noise that we took from the standard Gaussian distribution at time step t. So when we take this noise, we will multiply it with this standard deviation at time step t. So we will control the level of this noise. After that, we will add it to the weighted xt minus 1. By doing this, we will get the value of xt variable. So now let's use alpha t rather than the variance. So let's write it again. xt, x at time step t, it is equal to xt minus 1 times the square root of alpha t plus the square root of 1 minus alpha t times epsilon t, where the standard deviation at time step t, it is equal to the square root of 1 minus alpha t. You can find that from this formula. Now we can do the same thing for xt minus 1. It is also Gaussian distribution. The mean of this Gaussian distribution is xt minus 1 times the square root of alpha t minus 1 plus the square root of 1 minus alpha t minus 1 times epsilon t minus 1, which represents the noise that we took from the standard Gaussian distribution at time step t minus 1. And here we will multiply all these things by the square root of alpha t plus the square root of 1 minus alpha t times epsilon t, which is, as we said previously, the noise that we took from the standard Gaussian distribution at time step t. Now we will multiply xt minus 2 times the square root of alpha t minus 1 by the square root of alpha t. And we will multiply the square root of 1 minus alpha t minus 1 times epsilon t minus 1 by the square root of alpha t. And here is the result. Xt, it is equal to the square root of alpha t times the square root of alpha t minus 1 times xt minus 1 plus the square root of alpha t times the square root of 1 minus alpha at time step t minus 1 times epsilon t minus 1 plus the square root of 1 minus alpha t times epsilon t. Now this thing here, we can say it is just a Gaussian distribution with mean equal to 0. And the variance of this distribution, it is just alpha at time step t times 1 minus alpha at time step t minus 1, which is the standard deviation squared. And the standard deviation for this Gaussian distribution, it is this thing here, which is the square root of alpha at time step t times 1 minus alpha at time step t minus 1. We will call this Gaussian distribution k. And this thing here, it is also a Gaussian distribution, and we will call it y. The standard deviation for this distribution is the square root of 1 minus alpha at time step t. So the variance will be equal to 1 minus alpha at time step t, while the mean of this distribution will be equal 0. You should know that if you want to add two Gaussian distributions, you can directly add their means and their variances directly. So k plus y equal to this Gaussian distribution, where the mean equal to 0, because 0 plus 0 it is equal to 0, comma, and the variance, it is equal to the variance of k plus the variance of y. So alpha t times 1 minus alpha t minus 1 plus 1 minus alpha t. We will multiply alpha t by 1, and we will multiply alpha t by alpha t minus 1. Finally, the variance of this Gaussian distribution will be 1 minus alpha at time step t times alpha at time step t minus 1, which is equal to the square root of 1 minus alpha at time step t times alpha at time step t minus 1 times epsilon at time step t minus 1. This distribution represents k plus y. And we can write it in this way. Here the mean equal to 0. And if we want to write it, so we need just to put the standard deviation, which is the square root of the variance. So we will write the square root of 1 minus alpha t times alpha t minus 1 times epsilon t minus 1. So now xt will be equal to the square root of alpha at time step t times alpha at time step t minus 1 times x t minus 2 plus the square root of 1 minus alpha at time step t times alpha at time step t minus 1 times epsilon at time step t minus 1. And this thing here, it is just k plus y distribution. And we will do the same thing again and again. We will open this xt minus 2 variable and do the same procedure. And we will get xt minus 3, we will open it, and we will do the same thing until reaching x0. So here finally, the variable xt is equal to the square root of alpha t times alpha t minus 1 times alpha t minus 2 times alpha t minus 3 until alpha 0 times x0, which is our original image, plus the square root of 1 minus alpha t times alpha t minus 1 times alpha t minus 2 times alpha t minus 3 until alpha 0 times epsilon 0, which is the noise that we will get from the standard Gaussian distribution with mean 0 and standard deviation 1. So now we can say that we can get the value of xt directly from this Gaussian distribution if we just have the value of our clear image x0. So this distribution, it is just q of xt given x0. And here we will make alpha t times alpha t minus 1 times alpha t minus 2 times alpha t minus 3 until alpha 0 equal to alpha bar t. So now we can write our final distribution like this. Xt it is equal to the square root of alpha bar t times x0 plus the square root of 1 minus alpha bar t times epsilon 0. So now we don't need the joint distribution anymore. We could reach q of xt given x0 by using reparameterization trick, and we can use this distribution to give us xt directly. Thanks for watching. Hi, in this video we'll talk about variance schedule. Let's say that we have x0, which is our clear image. We will add noise to this image. Let's call it noise 1. Here, the level of this noise will be very small. And as we said previously, we will use the standard deviation of the Gaussian noise to control the level of the noise that we will add. In other words, the variance of this noise, it is very small. Let's say that the variance of this noise, it is equal to 0.0001. So now we have this distribution that we will use to pick the value of x1 variable. Now we are at time step 1. We will add noise 2 to our x1 image. And here the level of noise 2, it is greater than noise 1. Or in other words, the variance of noise 2, it is greater than the variance of noise 1. And the value of the variance of noise 2 will be equal to the value of the variance of noise 1 plus the step size. We will talk about how to compute the step size or variance difference later. So now we have this Gaussian distribution that we will use to get the value of x2 variable. We will get x2 at time step 2, and we will add noise 3 to this image. And here we will again increase the variance of this noise, or we will increase the level of the noise that we will add to x2. Now the variance of noise 3, it is equal to the variance of noise 2 plus the variance difference. So here, the variance of noise 3, it is greater than the noise 2, and the variance of noise 2, it is greater than noise 1. Let's say firstly, the variance of noise 1, it is very small value, which is, let's say, 0.0001. And let's say that the maximum variance that we want is 0.02, and the minimum variance is 0.0001. So we will compute the difference between these two things, and we will divide the results by the number of steps, which is 3. The result will be 0.0099. This is the amount that we will add to the variance of the previous noise to get the variance of the noise that we will add at the current time step. We will call this amount the step size. Okay, so firstly, the standard deviation is equal to the minimum standard deviation. So here the variance of noise 1 will be equal to the minimum variance, which is equal to 0.0001. And now we are at time step 1. We will add the step size to the previous variance. So we will get 0.0001 plus 0.0099. And now we are at time step 2. So again, we will increase the level of the noise. So here the variance of noise 3, it is equal to 0.0001 plus 0.0099 plus 0.0099, which is equal to the variance maximum value. Let's say that we want to make the maximum variance equal to 1. At this case, x3 will be just standard Gaussian distribution or normal distribution, where the mean equal to 0 and the standard deviation equal to 1. At this case, we will lose all the information about x2 value. Our x3 variable here, it is just pure noise without any information. We call this variance schedule linear variance schedule because here we are increasing the variance of the previous step by fixed amount in the current step, which is the step size. So here we are increasing the value of the variance linearly. We said previously that we will use alpha rather than the variance. So here, let's say that we want to compute alpha bar 1, alpha bar at time step 1. It is equal to alpha 1, which is equal to 1 minus the variance at time step 1. Now, let's say that we want to compute alpha bar 2, alpha bar at time step 2. It is equal to alpha 1 times alpha 2, which is equal to 1 minus the variance at time step 1 times 1 minus the variance at time step 2. And let's say that we want to compute alpha bar at time step 3, which is equal to alpha 1 times alpha 2 times alpha 3, which is equal to 1 minus the variance at time step 1 times 1 minus the variance at time step 2 times 1 minus the variance at time step 3. So now we learned how to compute the value of the variance at each time step and how to compute the value of alpha bar at each time step. Finally, we can use this formula to get the value of xt variable at any specific time step. This is the Gaussian distribution that we will use to get the value of xt. We can compute the value of alpha bar, and we have the value of x0. It is our clear image, and we can pick the value of epsilon 0 from the standard Gaussian distribution. So we can get the value of xt variable. Hi, previously we talked about linear variance schedule, and we could compute the value of alpha bar at each time step. In other words, now we are able to find the value of xt directly from x0. As we said previously, when we move forward from one time step to another, we will increase the variance or we will reduce the value of alpha bar. To make things more clear, let's say that we will move just 3 time steps forward, and let's say the step size equal to 0.1. As we said previously, alpha at time step t, it is equal to 1 minus the variance at time step t. So when we increase the variance, we will reduce alpha. Let's say firstly that alpha at time step 1, it is equal to 0.9. So alpha bar at time step 1 will be equal to 0.9 also. Now let's say that we are at time step 2. Here we will increase the variance by 0.1 by the step size. So we will reduce alpha by 0.1. So alpha at time step 2 will be equal to 0.8. Now let's compute alpha bar at time step 2, which is equal to alpha at time step 1 times alpha at time step 2, which is equal to 0.9. 0.9 times 0.8, and the results will be equal to 0.72. So as you can see here, alpha bar at time step 2, it is smaller than alpha bar at time step 1. Now we are at time step 3. So alpha at time step 3 is equal to the previous alpha, which is alpha at time step 2 minus 0.1, or the step size. The results will be equal to 0.7. Now let's compute alpha bar at time step 3, which is equal to alpha at time step 1 times alpha at time step 2 times alpha at time step 3, which is equal to 0.9 times 0.8 times 0.7, and the results will be equal to 0.5. So here, alpha bar at time step 3, it is smaller than the previous alpha bar, which is alpha bar at time step 2. But the problem here actually, as you can see here, the value of alpha bar will reach 0 quickly. Its value will be very close to 0 at time step 600. And when alpha bar it is very small, it means that we will lose most of the information from our original image. In other words, all the time steps after 600 time step, they will be useless. All of them will be the same, just noise without information. As you can see here, we will lose the information of our original image quickly when we use linear variance schedule. And here we lost actually almost all the information from our original image in time step 8. The rest of the time steps, they will be just noise. So to solve this problem, we will use cosine-based variance schedule. As you can see here in this schedule, the value of alpha bar will not decrease quickly. So we will not lose the original information quickly. And this thing, it is good for training our stable diffusion model, where most of the time steps, they will have some information about the original image. So now we have two variance schedules, linear variance schedule and cosine-based variance schedule. And as you can see here, cosine-based variance schedule is better than linear variance schedule. Thanks for watching. Hi, in this lecture we will talk about reverse diffusion. Previously we learned how to move forward from one step to another and how to add Gaussian noise at each time step. Now let's say that we have x3, which is noisy image. Now we want to remove the noise that we added to x2 to get x3, or in other words, we want to remove the noise that we took from this Gaussian noise 3 distribution and move back to x2. Or in other words, we need to find the distribution that we can use to get the value of x2 given the value of x3 variable. We call this distribution the target distribution. It is our target. This distribution will have all the possible values of x2 given the value of x3 variable. Now we will take the value of x2 variable and we will do the same thing again. We will try to find the distribution, the target distribution of x1 variable given the value of x2 variable. Now we will take the value of x1 variable from this distribution, and now we have the value of x1 variable. We will try to find the distribution of x0 variable given the value of x1 variable. We will pick the value of x0 variable from this distribution. The value of x0 variable that we took from this distribution will be something similar to our original image, to our clear image, x0. And here you should know that we should use very small step size. Or in other words, we should make the number of time steps very large. As you know, the step size, it is related to the number of time steps. When you increase the number of time steps, you will decrease the value of step size. So why we need to do that? Why we need to make the step size very small? To make things more clear, let's say that the number of time steps equal to 1000, which is a very large number. So the step size will be very small. By doing this, we will make sure that we will add very small level of noise in the first steps. By doing this, we will make sure that the target distributions for these time steps, they will be very good distributions. And that's what we will see later. As you know, firstly, we will add very small level of noise to our x0 variable. Now, the variance of noise 2 will be also very small, because here the step size it is very small, and the variance of noise 2 it is equal to the variance of noise 1 plus the step size. And because that the step size it is very small value, because the number of time steps it is very large, and because that the previous variance it is very small, so the variance of noise 2 will be also a very small value, which is the previous variance plus the step size. So when we increase the number of time steps, so we will increase the number of these good target distributions. Another thing that can increase the number of good target distributions is to make the maximum variance equal to small value. Like in this case, we will make it equal to 0.02. The maximum variance, it is the variance at time step t capital, and in this case t capital it is equal to 1000. So the maximum variance it is the variance of noise 1000, which is the last time step. By reducing the value of maximum variance, we will reduce the step size also. So by doing this, we will increase the target distributions. And even the last target distribution, which is the distribution of variable x999 given x1000, we can say it is also good, because the level of the noise that we added here it is not very large. The level of the noise, or the variance of the noise, it is just small value 0.02. But of course the previous target distributions will be better than this distribution. Now we will explain what is the meaning of good target distribution. Now let's say that we have the distribution of xt minus 1. We call this distribution prior distribution. We can use this distribution to get the value of xt minus 1 variable. Now let's say that we took xt minus 1, the value of xt minus 1 variable. Now we will add a noise to this xt minus 1. We can add a noise with large variance or a noise with small variance. A noise with large variance will remove large amount of information from xt minus 1. In other words, when we will take the value of xt variable from this distribution, this value will have very small information about the value of xt minus 1 variable. And the noise with the small variance will remove small amount of the information from xt minus 1. In other words, when we take the value of xt variable from this distribution, this value will have large amount of information about the value of xt minus 1 variable. Now, let's say that we added a noise with large variance. And here's the distribution that we will use to pick the value of xt. Now let's say that we took the value of xt variable from this distribution q of xt given xt minus 1. Here we will use this value xt to update this distribution based on this value, and we will call this the posterior distribution. As you can see here, this distribution isn't that good because we added large level of noise and we lost most of the information in xt value about xt minus 1 value. So the range of possible values for xt minus 1 variable will be large. It is like knowing the value of xt variable didn't make us certain about the value of xt minus 1 variable. So you can see this is very bad distribution. Now we will try to make this posterior distribution or target distribution better. Or in other words, we will try to reduce the range of possible values of xt minus 1 variable given the value of xt variable. Now we took the value of xt minus 1 variable from this prior distribution. Okay, now we will add a Gaussian noise with small variance. So now we have this distribution that we will use to get the value of xt variable. Now let's say that we took the value of xt variable from this distribution and we will update our prior distribution based on this value, based on the value of xt variable, and we will get this posterior distribution. You can see now that the range of possible values inside this posterior distribution, it is smaller than what it was before, which means that we are more certain about the value of xt minus 1 given the value of the variable xt, because the value of xt variable has large amount of information about the value of xt minus 1 variable. And as you can see here, the shape of this target distribution or this posterior distribution, it is very similar to the shape of any Gaussian distribution. In other words, when we decrease the variance of the Gaussian noise that we want to add at any time step, we are trying here to make the target distribution something similar to any Gaussian distribution. So from now on, we will treat any target distribution as Gaussian distribution. So here we didn't just decrease the range of possible values, but we also made the shape of the target distribution similar to the Gaussian distribution, which is very simple distribution. And that is what we meant by good target distribution. So now we can say that q of xt minus 1 given xt, it is just Gaussian distribution with the specific mean and variance. The mean and the variance of this distribution will depend on the value of xt variable. And now we will approximate this distribution. We will learn this distribution using a neural network. Okay? So here we will write p subscript theta of xt minus 1 given xt. It is just a Gaussian distribution. Here we will update the parameters of this neural network to find the best value for the mean and the standard deviation that it will make this predicted distribution similar to the target distribution. Here we will pass the value of xt variable and the time step that we are in right now to our neural network. And our neural network will try to predict a mean and the standard deviation. In the next video, we will learn how to find the target mean and the target standard deviation. And we will realize that we can make things more easier than this. Thanks for watching. Hi, in this lecture we will answer this question. How can we train our neural network? Previously we said that we will train our neural network to predict the target distribution, which is the distribution that will move us from xt to xt minus 1. As you can see here, this is the distribution that our neural network will predict, which is p sub theta of xt minus 1 given xt. This distribution, it is just Gaussian distribution. We have two hyperparameters for this distribution. The first one is the mean of the distribution. We will try to make this mean closer to the mean in the target distribution. We will try to learn what is the best value for this parameter based on xt and the time step that we are in right now. We will try to tune the parameters of our neural network to predict the best mean for the target distribution. We call these parameters theta. We will try to tune them to find the best mean. And we will do the same thing for the variance. We will pass xt and the step that we are in right now through our neural network. And our neural network will try to predict the best value for the mean and the variance. And here we passed the time step to our neural network to make our neural network able to realize the level of the noise that we added at this time step. This will help our neural network to realize the noise that we want to remove at this time step. Let's say that if the time step equal to 10, the level of the noise that we added in this time step, it is higher than the level of the noise that we added in time step 1. And the second thing that we will pass it through our neural network, it is x sub t. And our neural network will return the predicted mean and variance. We will use this mean and variance to create the predicted distribution. If the predicted mean and variance are very similar to the mean and variance of the target distribution, so this predicted distribution will be very close to the target distribution. And you should know that if t capital, which is the last time step, it is equal to infinity, at this case, the distribution of xt, it will be equal to the standard Gaussian distribution, where the mean equal to 0 and the standard deviation equal to 1. But actually we will make t capital equal to 1000, which is the best value. And we will make the maximum variance equal to 0.02. They did a lot of experiments to realize that. In general, the target distribution for any time step, it is just the distribution of xt minus 1 given xt. So now, why we put it x0 here? Here we will not give the value of xt variable only, but we will give the value of x0 variable, or in other words, our clear image. By doing this, we will be able to find the mean and the variance of the target distribution easily. And actually during training, we have our clear images. We will take them from our data set. We will call this clear image our reference image. But here we will have another problem. The mean of our target distribution will depend on xt and x0. And because that the mean will depend on the value of xt variable and the value of x0 variable, so we should pass the value of xt variable and the value of x0 variable and the current time step to our neural network. We can do that during training because we have the value of x0. But during inference, or when we want to use our neural network to generate images, we will not have the value of x0 because we want to create new images. In the previous lecture, we said that we will just pass the value of xt variable and the number of the current time step. So we will learn how to solve this problem and remove the value of x0 variable in the mean of the target distribution. Here we will use Bayes' theorem to get the posterior distribution, or q of xt minus 1 given xt and x0. Previously we said that we will give the value of x0 to find the posterior distribution easily. So why it is difficult to find the posterior distribution without the value of x0? To know that, let's apply Bayes' theorem. The distribution xt minus 1 given xt and x0, it is equal to the distribution of xt given xt minus 1 and x0 times the distribution of xt minus 1 given x0 divided by the distribution of xt given x0. We put it x0 here because it is difficult to find the distribution of xt if we don't have the value of x0. And it's difficult to find the distribution of xt minus 1 if you don't have the value of x0. But when we have the value of x0 here, we learned previously how to move directly from x0 to any time step. We talked about that in reparameterization trick lecture. We said that it is just Gaussian distribution. The mean of this distribution, it is just the square root of alpha bar t minus 1 times x0. Here we have x0. And the variance, it is 1 minus alpha bar t minus 1. And here also the mean of this distribution, it is just the square root of alpha bar t times x0. Here we have x0 also. and the variance, it is just 1 minus alpha bar t. And here, this distribution q of xt given xt minus 1 and x0, it is similar to the distributions that we got in the forward diffusion, but we didn't have the value of x0. But as we said previously in Markov chain lecture, xt will just depend on xt minus 1. The current step will just depend on the previous step. So we can remove the value of x0. And this thing, it is just Gaussian distribution. The mean of this distribution, it is just the square root of alpha t times xt minus 1. And the variance, it is 1 minus alpha t, which is also beta t. By using this Bayes theorem, we will get the posterior distribution or the target distribution. This Bayes theorem will update our prior knowledge, our prior distribution, which is q of xt minus 1 given x0, based on the value of xt. This equation here represents any Gaussian distribution. So, if we have a Gaussian distribution with a specific mean and a specific variance, it is equal to 1 divided by the standard deviation of this Gaussian distribution times the square root of 2 times pi times exponential raised to power minus 1 divided by 2 times x minus the mean of this distribution squared divided by the variance of this Gaussian distribution. Here x represents the variable that we will get its value from this distribution. For example, we will use this Gaussian distribution to get the value of the variable xt minus 1. So we will put xt minus 1 here. Now we will represent all these distributions, all these Gaussian distributions using this way. The mean of this distribution, it is the square root of alpha t times xt minus 1. We will put this mean in our equation. And the variance of this distribution, it is just 1 minus alpha t, or we can say it is beta t. We will also put it in our equation and we will get this thing here. And as you can see here, we will use this distribution to get the value of xt variable. So we will put xt in this place here. Now we have this Gaussian distribution. The mean of this distribution is the square root of alpha bar t minus 1 times x0, and the variance is 1 minus alpha bar t minus 1. We will put all these things in this equation and we will get this thing here. And we will do the same thing with this Gaussian distribution. The mean of this Gaussian distribution is the square root of alpha bar t times x0, and the variance is 1 minus alpha bar t. We will put all these things in this equation here and we will get this thing here. Here you might ask yourself why we didn't put 1 divided by the standard deviation times the square root of 2 times pi here in this place. The answer is easy. Here we will convert all these things into just one exponential and we will extract the mean and the variance of the target distribution from the power of this exponential. As you can see here in this equation, this thing here, we will not use it to find the mean and the variance of the target distribution. It is actually available in this place here. But as we said previously, we will convert all these exponentials into just one exponential. Here we will compare the power of this exponential with this equation, with the power of the exponential in this equation to compute the value of the mean and the variance of the target distribution. Finally, you will get the variance of the target distribution, which is equal to 1 minus alpha bar t minus 1 divided by 1 minus alpha bar t times beta t. And the mean of the target distribution, which is equal to the square root of alpha t times 1 minus alpha bar t minus 1 divided by 1 minus alpha bar t times xt. Plus the square root of alpha bar t minus 1 times beta t divided by 1 minus alpha bar t times x0. As you can see here, the mean of the target distribution depends on the value of xt and the value of x0. but we want to make the mean just depend on the value of xt. So what we should do? As you know, we have simple formula that will make us move directly from x0 to xt. We talked about this formula in reparameterization trick lecture. xt is equal to the square root of alpha bar t times x0 plus the square root of 1 minus alpha bar t times epsilon. So now we will extract x0 from this formula. x0, which is equal to 1 divided by the square root of alpha bar t times xt minus the square root of 1 minus alpha bar t times epsilon t. Now we will put this thing here in this place. So finally, the target mean will just depend on the value of xt variable. The target mean will be equal to 1 divided by the square root of alpha t times xt minus 1 minus alpha t divided by the square root of 1 minus alpha bar t times epsilon t. So now we just need to pass the value of xt variable and the number of the current step through our neural network, and our neural network will try to predict the mean of our target distribution. As you can see here, we don't need to use our neural network to predict the variance of our target distribution, because we know how to compute the value of alpha bar at any time step, and also how to compute the variance beta sub t at any time step. So we know how to compute the target variance, or the variance of the target distribution at any time step. So we will make our neural network just try to predict the target mean, or the mean of the target distribution. And because that we know how to compute the value of alpha t and alpha bar t, and we have the value of xt variable, so we will make our neural network just try to predict what is epsilon t. And that's what we will see in the next lecture. Now we learned how to find all the parameters of the target distribution. So now we will use the neural network to predict the noise that we will get from the standard Gaussian distribution, where the mean equal to 0 and the variance equal to 1. So our neural network will get two values here, xt and the time step number, to make our neural network able to realize the level of the noise that we added here. So, as you know, the mean of the target distribution is equal to 1 divided by the square root of alpha t times xt minus 1 minus alpha t divided by the square root of 1 minus alpha bar t times epsilon t. This thing is our target. We want from our neural network to predict this noise here. So here our objective, or our loss function, it is equal to the difference between the target noise and the predicted noise from our neural network squared. We will try to tune the parameters of our neural network to reduce the difference between the predicted noise and the target noise. Or in other words, we will try to train the parameters of our neural network to reduce the value of this loss function. By doing this, we will make the predicted noise similar to the target noise in the mean of our target distribution. PyTorch package will do all these things for us. It will tune the parameters of our neural network to reduce the value of the loss function, and making the predicted noise get closer and closer to the target noise. Thanks for watching. Let's now visualize the training process. Firstly, what is the meaning of epoch? The number of epochs means the number of times that we will pass it through our data set. Or in other words, the number of times that we will pass it through all images. Here in this case, we will pass through our data set a number of times. Inside each epoch, firstly, we will take a specific image and take a random time step and we will add the noise to this image based on the time step. After that, we will pass our noisy image and the time step of this image through our network, and our network will try to predict the epsilon or the noise, and we have the target noise that we added actually to our image. We will compute the difference. We will use PyTorch to tune the parameters of our network to reduce that difference. We will do the same thing for all images in our dataset. After passing through all the images, we will complete one epoch, and we will start with a new epoch. So here, at each epoch, we will pass it through all our images, and we will do the same thing again. We will specify specific time step for each image in our dataset, and we will add the noise to each image in our dataset based on its time step. As you know, we learned previously how to move directly from the original image x0 to x at time step t by using this formula here. And previously we learned how to compute the value of alpha t and alpha bar t. And as you know, we will take epsilon from the standard Gaussian distribution. So now we will pass these noisy images and their time steps through our U-network to predict the epsilon for each image, and we have the target epsilon for each image, so we can compute the loss, and we will try to reduce the value of the loss by tuning the parameters of the network. We will do the same thing again and again until ending epoch n. And here we will train our U-network for many number of epochs to reduce the loss values from the loss function as much as possible, because one epoch will not be enough, especially when your data set is difficult. Hi, in this video we'll talk about inference, and we will learn how to use our stable diffusion model. Let's say that we trained our stable diffusion model previously, and now we want to use it. So how can we do that? Previously we said that we will use our stable diffusion model to predict the target distribution, or in other words, it will try to predict the mean and the variance of the target distribution. And we found that we just need to compute the mean, and more specific, the epsilon inside the mean. Let's say firstly the xt, it is just a pure noise that we took from the standard Gaussian distribution. As you know, during inference time we don't have any data set, and we will start with a pure noise to generate artificial images. So when we will try to remove the noise using our network, we will not able to know what the clear image that we will end up with. Here we will predict the target distribution of xt-1 variable, and we will use it to take the value of xt-1 variable. Now we have the value of xt-1 variable. We will do the same thing again. We will try to predict the target distribution of xt-2 variable based on the value of xt-1 variable. We can repeat this process for any number of time steps, but it should be less than 1000 time steps. Let's visualize what we talked about earlier. Firstly, we will sample a Gaussian noise from the standard Gaussian distribution, let's say. And let's say here t capital equal to 1000. Now we have x1000. We will pass x1000, our noisy image, through our U-network. We will pass the embedding for the time step through our U-net also, and we will predict epsilon. We will use this formula here to compute xt-1. We will put the predicted noise here, and here we will put our noisy image x1000, and here we will predict x999. We will use this predicted distribution to get the value of x999. We will do the same thing again and again until reaching x0, and we will get good image. Let's say that we did the same thing again and again until reaching x2. Our noisy image now it is x2. We will do the same thing. We will also pass it through our unit and the embedding. For this time step we will predict the noise, and we will use this formula to compute xt-1, or in other words to find the distribution of x1 variable, and we will get the value of x1 from this distribution. And we will do the same thing to get the distribution of x0 variable, and we will take the value of x0 variable from this distribution. Here we will use the value of x1 variable that we will take from this distribution. We will pass it through our U network, and we will pass the embedding of time step 1, and we will get this noise. We will put the value of x1 variable and the predicted noise inside this formula to get the distribution of x0 variable. We will take the value of x0 variable from this distribution, which is this image here. Thanks for watching. Hi, in this video we'll talk about simple U network. Here they used this U network for segmentation task. Now, what is segmentation task? Let's say that we have this image. Now let's say that we want to classify each pixel on this image to a specific class. So we will pass this image to our U network. This network trained previously to do this task, and we will get the output from this U network. As you can see here, we classified each pixel in our original image to a specific class. These pixels here represents the road, and these pixels here represents these trees, and these pixels represents these buildings, etc. Here they used many different layers to create this simple U network. Now let's say that we resized our image and made its height and width equal to 572. Now we will pass this image through our U network. Firstly, we will pass our image through a convolution layer with a 3x3 kernel. What is convolution layer? Let's say that we have this image and we want to pass it through a convolution layer. Here is the kernel of our convolution layer. This kernel has trainable parameters. They trained these parameters previously to solve this task. As you can see here, we will firstly multiply this kernel with this part here. After that, we will multiply it with this part here. And what we will actually do here, we will multiply each parameter inside our kernel with the corresponding pixel in our image. After that, we will add all the results to obtain just one single value in the output. For example, let's multiply this part here in our image by our kernel. So 70 times 0 plus 129 times minus 1 plus 127 times 0 plus 115 times minus 1 plus 69 times 5 plus 134 times minus 1 plus 123 times 0 plus 95 times minus 1 plus 130 times 0, which is equal to minus 128. And as you can see here, we will slide our kernel from top left to bottom right of our image. And here's the output, which is the feature map. This feature map will have just the important thing in our image. And by important things, I mean the things that our kernel, our filter, says are important. And you should know that we will use more than one filter inside each convolutional layer. Here we took just one filter or one kernel for simplicity. Another thing that you should focus on is the width and the height of the output will be smaller than the width and the height of the input image. That's good, but all what we did previously, it is just multiplication and addition. So we will not be able to model nonlinear relationships by doing just this thing. So we need to use an activation function to handle nonlinear relationships. Here we will use ReLU activation function. We will pass our feature map through this activation function. This activation function will make anything less than 0 in our feature map equal to 0, and it will keep anything greater than 0 in our feature map as it is. As you can see here, this activation layer, it is very simple and doesn't have any trainable parameters. And it will make our neural network able to handle very complex data set. As you can see here, the width and height of the outputs reduced because of the convolutional layers. Now we will pass the output feature map through max pooling layer. This layer will condense the features in the feature map that our filter said they are important. And it will also reduce the width and the height of the feature map. The idea here, it is very simple. Like what we did previously, we will slide over our image, our feature map, and at each time we will take the highest number. So here we removed the features that our filter said they are not important. And as you can see here, the width and the height of the output, it is smaller than the width and the height of the input. So here we also reduced the width and the height of the feature map, but without using any convolutional layer. We just used max pooling layer. This layer doesn't have any trainable parameters, which means it will not increase the size of our network compared to the convolutional layer. And you should know that the convolutional layers inside this simple U network has many kernels or has many filters. Like in this case here, we have 128 feature maps, which means that the previous convolutional layer has 128 filters or 128 kernels. Each one will create its own feature map. We will do the same thing here until reaching this place. Here we will use a special layer, which is transpose convolution layer. Previously we said that the width and height of the output from any convolutional layer is smaller than the width and height of the input to the convolutional layer. Here in the transpose convolutional layer, the width and height of the output will be larger than the width and height of the input. For example, let's say that we have this very simple feature map. It is the input to our transpose convolution layer. And we have this filter, this kernel, 3x3 kernel. The first thing that we should do is to put the output. Here we want the output to be 4x4, 4 rows and 4 columns, while the input is 2x2. And here we put it padding around our output, because if we don't put it, we will end up again with 2x2. Here we will slide our kernel through the output, and each time we will multiply the kernel with the specific value from the input. You should know that we will remove all these paddings because they are not important. We just put them to make sure that the output shape will be 4x4. By doing this, we will get bigger feature map. We will do this thing again and again, and the width and height of our feature maps get bigger and bigger until reaching this place here. And as you can see here, these arrows, we call them skip connections. We will use them to join the low-level features with the high-level features. They found that doing this will make the training of our unit faster, and the results will become better. The last layer here, it is just convolutional layer, and the size of each kernel in this layer is 1 times 1. I know this layer, it is convolutional layer, but here the shape of the output will not be smaller than the shape of the input, but it will be the same as the shape of the input. This case will happen just when the size of the kernel equal to 1 times 1. Most of the time we use this layer with 1 times 1 kernel size to control the depth or the number of feature maps in the output. So we will apply each filter on each pixel in the feature map to make predictions for each pixel. We will use these predictions to decide the class that related with each pixel. Here in this course we will not use U-network for segmentation, but we will use it to predict the noise, the epsilon, in our noisy image. To do that, we need just to change the output layer, the final layer in our U-network, and we will learn that later. Thanks for watching. Hi! In this lecture, we will talk about unconditional U-network for noise prediction. By unconditional, it means that we will not be able to control what our stable diffusion model will generate. We will use this U-network to predict the epsilon or the noise. And as you know, we have beta t, alpha bar t, so we can create the target distribution that we will use to get the value of xt minus 1 variable. Let's say that we have this image which represents the value of x1 variable. Now you should know that any colorful image has 3 channels: red channel, green channel, and blue channel. These channels will create the colors in our image. In other words, we will represent each pixel in our image by 3 values. So when we want to add a noise to our pixel, we need to add a noise to each one of these values, which means that we want to, from our U-network, to find the noise for each one of these 3 values for each pixel. In other words, the epsilon will also have 3 channels, and the width and height of the epsilon should be equal to the width and height of the input image also, to make sure that we will predict the noise for each one of these pixels in our input image. But in the case of grayscale images, these images will have just 1 channel. In other words, we will represent each pixel in our image by just 1 value. So when we want to add a noise to a specific pixel, we will add a noise to its single value. In this case, the predicted epsilon will have also just 1 channel, and the width and height of epsilon will be equal to the width and height of the input image. Previously, we said that we need to make our neural network, our U-network, able to realize where we are right now, at which time step we are now. To do that, we will pass the time step that we are in right now to our U-network. How can we do that? Firstly, you should know that it's not a good idea to pass the number of time steps that you are in right now directly to your U-network, because it will affect on the training. You should convert this number into a vector of values using positional encoding function. This function will create a unique vector of values for each time step. Each positional embedding vector will have the information about the position of its time step. We will join this positional embedding vector with the output from each layer in our U-network. By doing this, we will make sure that our neural network is able to know where we are right now and the level of noise that we added here, and we want to remove it. Here in this case, x1, it is at time step 1, so we will pass the positional embedding vector of time step 1 to our neural network, and our neural network will predict the epsilon. We have beta t, alpha t, Now we have epsilon, beta t, alpha bar t. We can use them to create the target distribution of variable x0, and we will take the value of x0 variable from that distribution. The last thing that we should talk about is how to control the number of feature maps of the output from our U network. If we want to make our epsilon has just one feature map, one channel, in this case, we should make the number of filters of the last layer in our U network equal to one filter. This one filter will create one feature map or one channel, which represents our epsilon. If we are dealing with colorful image and we want epsilon to have 3 channels, so we should make the number of filters of the output layer equal to 3. Each filter will create one channel or one feature map. So we will get finally 3 feature maps or 3 channels. In the next video, we will talk about positional encoding and how it works. Thanks for watching. What is positional encoding? Firstly, you should know that this wave here, it is sine wave. The highest value in this wave is 1. And the lowest value in this wave is -1. This axis here, it is time step axis. Here we have all the time steps from time step 1 to time step 1000. For each time step, let's say this time step here, t, we have specific value in this sine wave, which is this value here in this y-axis. But the problem here actually, this value will not be unique. Let's say that this time step, it is time step 10. And let's say that this time step here, it is time step 400. This time step will have the same value of time step 10. As you can see here, the value of this time step, it is similar to the value of time step 10, like this, in this y-axis, in our sine wave. So how can we solve this problem? How can we make unique value for each time step using this sine wave? To do that, we will make just this part here from our sine wave cover all these time steps. Okay? We can do that by reducing the frequency of this sine wave. Now this part here covers all this region from 1 to 1000 time step. And we can say that we will get a unique value for each time step from 0 to 1000. Let's say that, for example, time step 1 will be equal to 0.001 in the y-axis. Time step 2 will be equal to 0.0011 in the y-axis. The last time step, which is time step 1000, will be equal to 1. As you can see here, 1000 will be equal to 1 on y-axis, like this. Now we have a unique value for each time step. As we said previously, we want to make our U network able to know where we are, at which time step we are right now. Let's say that we passed this time step, the value of time step 1, which is 0.001, to our neural network. It will be difficult for our neural network to understand that we are at time step 1. Actually, here we reduced the range of possible time steps. So now our neural network is focusing on a specific region of possible time steps. Let's say this region here. Okay, and let's say that this region has two time steps, T1 and T2. But our neural network is uncertain about which is the real time step that we are in right now, because the difference between these two time steps is very small. So now we can say that just one unique value for each time step will not give us the precise time step that we are in right now. Now we will use this cosine wave. The highest value in this wave is 1, the lowest value in this wave is -1. We will reduce the frequency of this wave like what we did previously to make this part here cover all the range between 0 and 1000. And this is, and as you can see here, this yellow curve cover all the range between 1 and 1000 time steps. Now we will do the same. Here time step 1 will be very close to 1 in the y-axis. We can say that time step 1 it is something in this place here. So in y-axis it will be very close to 1 value. And as you can see here, let's say that the value of time step 1 it is 0.999. Now we will do the same thing for time step 2. Time step 2 on y-axis will be equal to 0.998. Here we didn't solve our problem because the difference between these two values in this positional embedding vector is very small, like in the previous case, So our neural network will not be certain about the real time step that we are in right now. Why? Because the difference between these two things that we added here, it is very small. So now what we will do here, actually, we will increase the frequency of this yellow curve. Actually, this yellow curve, it is just cosine wave. If we want to complete this curve, it is just cosine wave, okay? But with very low frequency. Now, what we will do, we will increase the frequency of this yellow cosine wave. By doing this, it will get closer to this cosine wave. The frequency of this cosine wave will get closer to the frequency of this cosine wave. As you can see here, in other words, it will complete one cycle quickly compared to the previous one. As you can see here in this pink cosine wave, it will move down quickly compared to the yellow cosine wave, like this, and it will move up quickly compared to the yellow cosine wave. So now, if we want to check the value of time step 1 for this pink curve, pink cosine wave, the value of T1 will be 0.9, let's say 0.9. So now let's check the value of time step 2, and it will be equal to 0.8. You can see the difference between the value of time step 1 and time step 2. It is greater than the difference in the previous case, okay, because we increased the frequency of this yellow wave. So when our a neural network sees this positional embedding vector, firstly, it will see this value 0.001. So our neural network will be sure that our real time step is within a specific range. Let's say this range, within this specific range that has time step 1 and time step 2. And now when our neural network sees this value 0.9, it will be certain that it is time step 1, because now the difference between time step 1 and time step 2, it is more clear for our neural network. Okay, that's it. Okay, that's the main idea behind positional embedding vector. Actually, we can add many other values to this positional embedding vector by doing the same procedure. We used previously cosine wave, so now we will use sine wave, and the frequency of this sine wave will be higher than the frequency of this cosine wave, so it will move faster than this cosine wave, pink cosine wave, like this. As you can see here, we have this green sine wave, and it is faster than this pink cosine wave. We will use this sine wave to add another unique value for these positional embedding vectors to make our neural network more certain about each time step. Thanks for watching. Hi, in this lecture we will talk about conditional U network. Here in this stable diffusion model, we will be able to control what our stable diffusion model will generate. So how can we do that? There are many different things that we can use for conditioning, like semantic map, text, representations, and images. Let's say that we want to create an image using our stable diffusion model based on a specific text. So how can we do that? Firstly, we will pass this text through language model. This model will convert this text into a vector representation, or we can call it text embedding, which is a vector with many numbers that represents what our language model thinks about this text. Now we want to fuse this vector representation of our text with our U network. How can we do that? One way to do that is by using cross-attention blocks. We will put these blocks inside our U network. These blocks will make our U network able to focus on a specific region in the feature map and based on our text. Let's say that we passed this text here, the dog on the car. Now we will convert this text into text embedding, and we will fuse this embedding with our U network. Now we will do reverse diffusion to create an image based on this text. Let's say that our stable diffusion model generated this image, a dog on the car image. Now let's change one word in this text. Let's change dog to cat. We will convert this text into text embedding, and we will pass it through our U network, and we will do reverse diffusion to create an image based on this text. As you can see here, this image, it is not different from the previous image. Here our stable diffusion model just changed this dog to cat, and this thing happened because of the cross-attention blocks that we added to our U network, which made our neural network able to know the region that we should change based on our text. Now you might ask yourself, how can we control the importance of the guidance or the condition in the generated image from our stable diffusion model? To do that, during training, we will not just predict the epsilon based on the input image and the time step, but also with the condition. Let's say that this condition is y. It might be text, image, etc. Here we will train our stable diffusion model in two states, conditional and unconditional, and we will decide that randomly during training. In other words, sometimes we will pass the condition to predict the epsilon, and sometimes we will not pass the condition to predict epsilon. Why we did that? We did that just to control the importance of the condition during the inference time. Now let's talk about the inference. How can we control the importance of the condition during the inference time when we want to use our stable diffusion to generate images after training? We will balance between the condition and the randomness by using guidance scale parameter. Firstly, we will pass xt, the time step that we are in right now, and the condition, and we will get epsilon value. And we will do the same thing, but now without condition. We will pass the value of xt and the time step that we are in, but we will not pass any condition to our neural network, and we will get the predicted epsilon. Now we have this parameter here, S, which is guidance scale parameter. We will use it to control the importance of the condition in the generated image. When we increase the value of this parameter, the weight of the epsilon that created based on our condition will increase, and the weight of the epsilon that created without any condition will decrease, which means that our generated image will follow our condition strongly. Actually, this graph here represents the forward diffusion and reverse diffusion. But what are these two things here? E and D. This thing here we call it encoder, and this thing here we call it decoder. Both of them will create variational autoencoder. What is the advantage of this variational autoencoder model? This model, we will not train it during training our U network. It is a pre-trained model. They trained this model previously to do the following task. Firstly, the encoder will compress our input image. Let's say that our image, it is very high resolution image. Let's say that the width of the image is 1000 and the height of the image is 1000. Which means if we want to pass this image directly through our U network, our training process will take long time. And the inference time will be very long because, as you know, we will take many time steps in reverse diffusion to generate high resolution image, and at each time step we will use our U network. So we will reduce the size of this image by using the encoder of our variational autoencoder. This Z here, it is our compressed image. We used this encoder to convert our input image to this new representation, which has the most important thing in our input image. And the size of this new representation, it is very small compared to our input image. In other words, the width and height of this image are very small compared to our input image. So when we pass this new representation through the decoder of the variational autoencoder, this decoder will be able to reconstruct our original image from this new representation. So now we reduced the size of our input image using this encoder. We will do the forward diffusion and we will get Z capital T, or you can get Z at any time step that you want. In other words, we added noise to this new representation of the input image. Now what we will do actually, we will use our stable diffusion model to remove the noise from this Z capital T. We will remove the noise from this Z capital T gradually in a reverse diffusion process to get Z, which is the compressed representation of our input image, our clear image. And we will use the decoder from the variational autoencoder to convert this predicted compressed representation to high resolution image. So now by making our stable diffusion model trying to generate compressed representation with small width and height, we will make the training time and the inference time very small. Thanks for watching. Hi, in this lecture we will learn how to build unconditional diffusion model. Firstly, we will download the necessary packages. So we will type !pip install diffusers package, datasets package, transformers package, accelerate package, ftfy package, pyro package version 9.0.0. And here in this code we will use the GPU to make the training faster. So we will click on this runtime, we will click on change runtime type, and we will choose GPU. After that we will click on save. We will click on this symbol here. We will run this cell. Now let's import the packages that we want to use in this code. Firstly, we will import NumPy package as MP. We will use this package to create arrays. And here we will import torch package. As we said previously, we will use PyTorch to build and train our network. And here we will import torch.nn.functional as f. We will use it to decide the loss function that we will use during training. And from matplotlib we will import pyplot as plt. We can use this library to visualize anything that we want. And finally from pil we will import image. Okay, we will run this cell. So we will import all these things. Now we will learn how to download our dataset that we will use to train our neural network. Firstly, from datasets package we will import load dataset. Okay, and we will use this load dataset class to download our dataset. Here we will download the dataset from Hugging Face community. And here we will use Smithsonian's butterflies subset. And as its name suggests, it has images for butterflies. And here we made this split argument equal to train because this load dataset will return two datasets. Training dataset and testing dataset. And here we want just the training dataset. Okay, so we will take just the training dataset. Now let's run this cell. And here's our dataset. In this dataset we have 1000 images. And for each image we have many different things. as you can see here, like the name, the gender, the region, etc. And of course the image itself is also available here. So now if we want to display just one image, how can we do that? Actually the images are available in this image feature. Okay, so we will type dataset and we will specify the feature that we want from our dataset, which is image, this one here. So this feature has all the images in our dataset. We will select one of these images. Let's say we want to display the image 100. Okay, so let's run this cell. And that's it. As you can see here, here is our image. It is butterfly image. Now you should know that 1000 images, they are not enough to train our neural network. So we should increase the number of images. How can we do that? We will do something called data augmentation. To do that, we will import the transforms class from Torch Vision package. Okay? Now firstly we should resize our images to a smaller size, like 128 times 128. Here we will make the width and height for all images in our data set equal to 128 times 128. Why? Because we need all the images to be the same size before passing them through your neural network. When you decrease the value of image size, you will make the training faster. Why? Because the size of the images that you will pass through your neural network will be smaller. As we said previously, we will use transforms class to do data augmentation. The first thing we will do, like what we said previously, we will do resizing. So we will type transforms.resize, and here we will pass the new size of our images, which is image size. So the size of the height will be 128 and the width will be 128 also. And here we will apply another transformation on our data. Here we will flip our images randomly along a horizontal axis. By doing this, we will increase the training images. So we will type transforms.random horizontal flip, and you can also rotate your data randomly, but I didn't use this augmentation. And here we will convert our images into PyTorch tensors. As you know, PyTorch will create our model, so we need to pass PyTorch tensors through our model. It is not possible to pass NumPy arrays through our model because our model is created using PyTorch library. Finally, we will do normalization. As you know, each pixel can take a value between 0 and 255. And it is not good to pass an input with very large numbers. So we need to normalize our images, our pixels. And we will do that by normalization. We will make the value of each pixel between -1 and 1. And how can we do that? We need to use transforms.normalize, and here we firstly should pass 0.5, and here we should pass also 0.5. It is something good for training our neural network. Now, how can we apply all these transformations on our dataset? To do that, firstly we should create this function, transform function. This function will take the examples, or in other words, our dataset itself, before doing any transformation. Here we will take the images from our data set. We will pass it through each image, okay? And we will do the following. We will convert the order of the color channels for each image to be something like this: red, green, and blue. Why we need to do that? Because it is the correct order of these channels. But when they store them, the order will be BGR, which is not correct actually. And here we will do this thing for each image in examples. And after changing the order of the color channels for each image, we will pass each image through all these transformations that we talked about previously. And we will store each image after applying all this transformation on it in this list. Actually, this examples variable, it is just a small version of our data set. And we also call it a batch of samples. This transform function will apply automatically when we want to create a batch of samples. And we will talk about that later. Finally, this list that will have all the new images after applying all these transformations, we will put it in this dictionary. To make things more clear, let's say that we have a batch of samples, and let's say this batch has around 3 samples. Inside each sample we have an image, and here we will extract the images from these 3 samples. We will change the order of the color channels for each image, and we will apply all the transformations on each one of these images, and we will put the results in a list, and we will create a dictionary. The key of this dictionary is images. We will use this dictionary to get the images after applying all the transformations. PyTorch will use this transform function automatically when we want to get a batch to train our neural network on. And by using it, we will be able to increase the images that our neural network will see, because here we will apply data augmentation during training. And now we will type dataset.setTransform, and here we will pass this function. By doing this, we will make sure that we will apply this transform function on our batch before passing it through our neural network. But why we need to pass a batch of samples rather than just one sample at each training step? The answer is easy. As we said previously, PyTorch will compute the values that we will use to update the weights of our neural network. And when PyTorch uses many samples, or in other words, a batch of samples at each time to compute these values, so these values will be more accurate than using just one sample to compute them. And by doing this, we will make the training faster. Now we will create our data loader. This data loader will convert your data set into batches. Each batch will have many images. Okay? So we should specify the batch size. Let's say that the batch size equal to 16, okay? Which means that each batch will have 16 images or 16 samples. And here we will create our data loader. Train data loader equal to torch.utils.data.data-loader. And here we will pass our data set, and we will specify the batch size, which is this one here. And here we will make shuffle equal to true, which is also important for training. Now we will create our neural network. Firstly, we will import unit 2D model from diffuser's package. Here we will specify the device that we will use, and as we said before, we will use our GPU, so we should type CODA here. Now let's create our model. This unit 2D model class from diffusers will make things very easy for us to create our neural network, our U network. So firstly we should type model equal to unit 2D model, and here we will open these parentheses, and here firstly we should pass the size of our image or sample size. It is equal to image size, which is equal to 128, and here we should specify the number of channels in the input, which is a 3. Our image, it is colorful image with 3 channels, red, green and blue, and the number of output channels, or the number of channels in the output from this U network, it is also 3, and we talked about this thing previously. The number of the feature maps in the predicted noise should be 3, and here we will specify the number of ResNet layers inside each block in our network. So now what is ResNet layer? As you can see here, this is ResNet layer, which has convolution layer and ReLU activation function, and it will also have skip connection that it will add the input and the output from ReLU layer. What is the advantage from this ResNet layer? This ResNet layer will solve the problem of gradient vanishing. What is gradient vanishing? When you increase the number of layers of your neural network, or in other words, make your neural network deeper. By doing this, when you want to update the weights of our neural network, you will start with the final layer or the output layer, and you will move backward. The values that you will use to update the weights of the layers of your neural network will get smaller and smaller during moving backward, which means that we will not be able to update the weights of the earlier layers of our neural network, because the values that we will use to update the weights of these layers will be very small values. ResNet layer will solve this problem by using these skip connections, which will create a direct path between the input and the output. We will use this ResNet layer inside our U network to solve the problem of gradient vanishing. We will specify the number of layers per block, which is 2 in this case. Here we will specify the number of the feature maps that we will get from each block in our U network. The first block will return 128 feature maps. The second block will return 128 feature maps. The third block will return 256 feature maps. The fourth block will return 256 feature maps. The fifth block will return 512 feature maps. The last block will return 512 feature maps. You should know that these out channels just for this part here, while this part here will just be the reverse order of these out channels. So the number of channels of the first block in this part here will be 512, the second block will be 512, the third block will be 256, the fourth block will be 256, the fifth block will be 128, and the sixth block will be 128. And of course, the last layer in our U network will return 3 channels. Now we have two things that we should specify here. We have down blocks and up blocks. Here we have all these down blocks. The first down block, it is just down block 2D, which is regular ResNet downsampling block, which has a convolution layer, activation layer, pooling layer, and it also has a skip connection. And we will use them to create ResNet downsampling block. And the same thing in the second block, the third block, the fourth block, and here the fifth block, it is attention down block 2D. This block will also have special improvements. This block will do spatial self-attention. This self-attention mechanism will give our neural network the ability to focus on the most important regions inside our input image. The number of parameters inside this attention down block 2D will be very large if the width and height of the feature map that you want to pass it through this block are very large. For this reason, we put this attention down block 2D in this place here, where the width and height of the feature map that we want to pass it through this attention down block 2D will be very small. Because here we passed our input image previously through many down block 2D before passing it through our attention down block 2D. And after each down block 2D, the width and height of the feature map, of the input feature map, will get smaller and smaller. And here we have down block 2D also. Now we have up block types. Okay, here we have up block 2D, which will have transpose convolution layer and also skip connections, activation functions, etc. And here we will use attention up block 2D. This block will also do spatial self-attention mechanism, and we put this block here for the same reason that we said previously when we talked about attention down block 2D, because the width and height of the input feature map will be very small here. So the number of parameters inside this block will be also very small, and the time that we need to apply this block on our input feature map will be very small. And we have all these up blocks 2D. Now that is our model. It is very simple. Diffuser's package makes it easy for us to create it easily. Now we will send our model to our device, which is our GPU. By doing this, we will be able to train our model on our GPU, which will make the training faster. Now we will specify the noise scheduler. Firstly, we will import DTPM scheduler from Diffuser's package. Okay, and now we will use this scheduler. Firstly, we should specify the number of training time steps, and we will make it equal to 1000. And here we should specify beta scheduler, and we will make it squared cosine CAPV2. Okay. Now we have the noise scheduler that we will use it to add the noise to our image or input image. Here we will create the optimizer. This optimizer will be responsible about updating the weights of our neural network, and based on the values that our PyTorch give it to us. It will give these values to the optimizer, and the optimizer will update the weights of our neural network based on these values and on the learning rate. So optimizer equal to torch.optimizer.AdamW. There are many different types of optimizers, and here we use this one. Here we will pass the parameters, the trainable parameters of our model to this optimizer, and we will specify the learning rate, and we will make it something small, let's say 0.0004. Here we will create this losses list, okay, and here we will create this loop. We will activate this loop 100 times, which means we will train our neural network on 100 epochs. And for each epoch, we will pass it through each batch in our trained data loader. Our trained data loader will give us the batch, okay, and we will extract the images from this batch, and we will send them to our device, our GPU. Now we have our clean images. That's good. Now we will create our epsilon, which is the noise that we will get from the standard Gaussian distribution. Noise is equal to torch.random, and here we will pass the shape of our clean images. So the shape of the noise will be similar to the shape of our clean images, and we will send this noise to our GPU. The first dimension of our clean images, it is the number of images. How can we extract it? Clean images.shape, and here we will take the first dimension. So now we have the batch size, or the number of images in the batch. Now what we will do actually, we will take random time steps. Time steps equal to torch.randInteger. As you know, the time steps, they are integer numbers. The range of the values between 0 and 1000. We made number of training time steps equal to 1000. And here we will pass the batch size. For each image in our batch, we should have a time step. We will create time step for each image in our batch, and finally we will send our time steps to our GPU. Okay. Now we will create our noisy images. Noisy images equal to noise scheduler.add noise, and here we will pass our clean images and the noise and the time steps. Okay, now we have our noisy images. We will pass them through our model. We will pass the noisy images, the time steps, and we will get the predicted epsilon. Okay, like what we said previously. Here we will use mean squared loss function to compute the loss, the difference between noisy prediction and noise, and we will get the result loss. We will do back propagation to compute the values that we want to use to update the weights of our neural network to reduce the difference between the predicted noise and the real noise. And we will add the value of the loss to our losses list. Okay, now the optimizer will use these values to update the weights of our neural network. So how can we do that? We should type optimizer.step. So now we updated all the weights. We will delete all these values inside the optimizer by doing the following: optimizer.zeroGradient. Let's run this code. Now the training finished. Let's use our stable diffusion model that we trained. Firstly, we should import DDPM pipeline from diffusers package. This pipeline will make it easy for us to use our unconditional diffusion model. So now we will type image pipe equal to DDPM pipeline, and here we will pass our model, our U network. So unit argument equal to our model, comma, and here we will pass our noise scheduler. So scheduler equal to our noise scheduler. Now we will use this pipeline to generate new images. So we will type image pipeline, and here we will pass the number of inference steps. We will start with the x1000 times step 1000, and we will move backward to x0. We call this process reverse diffusion process. Finally, we will get pipeline output, and here we will type pipeline output dot images, open these square brackets, and here we will put 0. By doing this, we will get our new image. Let's do it. And here's our image. This image is not available in our dataset. This image created completely using our diffusion model. If you want to generate another image, you can run this cell again and see another image. Here is another image created by our diffusion model that we trained previously. You can also reduce the number of reverse diffusion time steps. Let's make it 400, which means that we will move 400 time steps from time step 1000 to time step 600. By doing this, we will make the diffusion process faster, but you might get low quality image. Now let's say that you want to save your unconditional diffusion model. How can we do that? We will type torch.save, and here we will type model.state dictionary like this, and here we will pass the name of the file that will represent our model. We will run this cell. Now we saved our stable diffusion model. You can find it here in this place. We will click here, and here is our stable diffusion model. If you want to download this model, you just need to click on download. Okay? Thanks for watching. Hi everyone, in this video we will learn how to use any pre-trained model from Hugging Face community. Firstly, you should know that there are many different models in the Hugging Face community, and you can use any one of them, but you should have an account in Hugging Face community to do that. Firstly, like what we did in the previous lecture, we should change the runtime of our notebook, and we will use our GPU like this. Now we will download diffusers package and datasets package like this. Now we should log in to our Hugging Face account. How can we do that? Firstly, we should import notebook login from Hugging Face hub. After that, we will type notebook login like this, and we will run this cell. Here you should put your token. How can you create your own token? So to do that, we should go to our account, and we should generate our own token. Click on this place here, and click on edit profile, access token, and here you should copy your token and put it here in this place. After that, you should click on login. That's it. Now you can download any pre-trained model from Hugging Face community. These pre-trained models are trained previously on specific tasks. Let's firstly import the packages that we want to use. We will import NumPy, Torch, and we will import torch.nn.functional as f, and Torch Vision, and we will import load data set from data sets, and we will import DDIM scheduler and DDMP pipeline from diffusers package, and we will import pyplot from matplotlib as PLT, and we will import image from PIL, and we will import transforms from torch vision. We will run this cell. Here we will use our GPU if it is available, otherwise we will use the CPU, which is much slower than our GPU. Okay. In this lecture we will take this pre-trained model, DDPM bedroom 256 model. Okay. So we will copy this model, and here we will download this model from Hugging Face community. So we will type DDPM pipeline from pretrained, and here we will pass the name of the model, of our pre-trained model. After that we will send this pipeline to our device that we want to use. As you can see here, we will download this model. This model will generate images for bedrooms. Now we should know that they found it's not important to move 1000 time steps in reverse diffusion to get a good image. You can do that with just a few steps. How can we do that? Firstly, we will download the scheduler that they used to train this model, DDPM bedroom model. To do that, we will type scheduler equal to DDIM scheduler.from pretrained, and here we should pass the name of our model that we want to use. By doing this, we will get the scheduler that they used to train this model, this diffusion model. Let's run this. Now we will set the time steps. So we will type scheduler.set time steps, and here we will make number of inference steps equal to 40. So we need 40 time steps to do reverse diffusion, to move from time step 1000 to time step 0. So let's see the time steps that we have right now. As you can see here we will jump directly from time step 1000 to time step 975, and we will jump from 975 to 950 time step, and we will jump from 950 time step to 925 time step. So now the number of time steps that we need to move from 1000 time step to 0 time step, it is very small, and the results will be good also. So now how can we use this scheduler? Firstly, we will create our image, which is, firstly, it is just pure noise. We will send it to our device, and the width and height of this image is 256. Why? Because our pre-trained model, this pre-trained model trained previously on images with 256 width and height. So here we should make it 256 width and height. Okay. And this pre-trained model trained on colorful images. So each image will have 3 channels. This one here, we will make it equal to 1, okay, like this, which represents the number of images in the batch. As you know, if we want to use our model, if we want to pass anything to our model, we should pass it in form of batch. So we have a batch with just one image, which is this image. Okay. Here we will not use our simple pipeline to generate the image. Here we will use a more flexible way, but you can use our previous way by using our simple pipeline to generate the image. Now we will create this loop here. We will pass it through the time steps that we have. We will start from this time step, and we will move in reverse order like this to reach time step 0. Okay. Now we will prepare the input to our model. How can we do that? We will type scheduler.scale model input, and here we will pass the input, which is this pure noise, and the time step. Now we don't need to train our model, so we should use it inside this context manager. So we don't need to compute any values to update the weights of our model. Okay, now, as you know, we have this image pipeline and our pre-trained model inside it, inside this pipeline. We will use our pre-trained U network, which is inside this image pipeline. We will pass the model input and the time step that we are in right now to this U network, and we will take the output from this U network, this pre-trained U network, which is our noise prediction or our predicted epsilon. Now we will do reverse diffusion. So we will type scheduler.step, and here we will pass the predicted epsilon, the current time step, and the noise. Okay, so we will remove this predicted noise, predicted epsilon from our noisy image to generate new image. Now we will make the noise equal to the output from our scheduler or scheduler output. Okay, so now we reduced the noise inside our input a little bit, and we will do the same thing again and again until reaching time step 0. Okay, now we will run this loop, and now we will take x0, our clear image, from our scheduler by doing this. x0 equal to scheduler output dot predicted original sample. Here we will get a batch with just one generated image. We will take this image, so we will open square brackets and we will put 0. Okay, like this. So we have our clear image. We will reshape this clear image so we can visualize it. Here we will change the order of the dimensions. Previously it was the channel dimension or the color dimension, after that the height dimension, and finally the width dimension. Here we will make it like this: the height dimension, after that the width dimension, and finally the channel or the color dimension. We will do that by using permute method. And here we will type the order of the dimensions that we want. Here 1 represents the height dimension, and 2 represents the width dimension, and 0 represents the channel dimension. Firstly, we want to put the height dimension, so we should type 1, comma. After that we want the width dimension, so we will put 2, comma, and finally we want to put the channel dimension here, so we will type 0. As you know, we normalized our image, so we should change the values of the pixels to make them between 0 and 255 again. How can we do that? Here we will make any value greater than 1 in our image equal to 1, and any value lower than -1 in our image equal to -1 by using clip method. We will multiply all the pixels in our x0 image with 0.5, and we will add 0.5. So now all the pixels, the values of all pixels between 0 and 1, we can now multiply them with 255. Just something similar to bedroom. The quality is good with just around I think 40 steps. Thanks for watching. Hi, in this lecture we will talk about Repaint algorithm. Let's say that we have a pre-trained diffusion model. This diffusion model will generate images for faces. Of course, we will start with a pure noise from the standard Gaussian distribution. We will start from time step 1000, and we will do reverse diffusion process to generate x0. Firstly, as you know, we will pass xt and the current time step through our U network, and our U network will return the predicted epsilon. We will use this predicted epsilon inside this Gaussian distribution to get the value of xt minus 1 variable, and we will reduce the value of time step by 1, and we will pass them again through our U network. So now we moved one step backward. We will do this again and again until reaching x0, our clear image. So now we have this generated image x0. Now let's say that you don't like the right part of your generated image. So firstly, we will remove this right part. Now this Repaint algorithm will try to complete this part by using our diffusion model, our pre-trained diffusion model. But how can we do that? How this Repaint algorithm works? Now we have x0 known, the known region, and x0 unknown, which is the unknown region of our image that we want to complete. And we will call this image x0 with mask. Okay? Now we will use this x0 with mask to move to time step t. We will use this Gaussian distribution to do that, and we will use it to get the value of xt variable. Now what we will do, we will pass the value of xt variable through our U network, and of course we will pass also the current time step. We will get the predicted epsilon, the predicted noise. We will use the predicted noise beta t, alpha bar t, alpha t, xt, and epsilon t to generate a Gaussian distribution that we will use to get the value of xt minus 1 variable. Now we will take just the unknown part from xt minus 1 variable. Here our diffusion model will automatically try to harmonize the unknown part of xt minus 1 variable with the known part. Our diffusion model will do this inherently during finding and removing the noise from xt variable. So now we can say that the unknown part of xt minus 1 variable, it is better than the unknown part of xt variable. And as you know, we have x0 with mask, which is this image here. We will use it with epsilon 0 that we will get from the standard Gaussian distribution, and the time step t minus 1 and alpha bar t minus 1 to create this distribution that will move us directly from x0 with mask to xt minus 1 with mask. We will take just the known part of xt minus 1, which is this area here, but after adding a noise to move to time step t minus 1. And as we said before, we will take just the known part of xt minus 1. But why we didn't took xt minus 1 known from this distribution from our diffusion model? We know this region, so why we need to use our diffusion model to predict this region in the first place? We just need to use our diffusion model to find the unknown area based on the known area. We will combine this known part with the unknown part of xt minus 1 that we got from this distribution and based on our U network. And as we said previously, this unknown part that we got based on our U network will be better than the unknown part in the xt minus 1 with mask variable that we will get from this distribution. As you know, the unknown part of xt minus 1 with mask variable, it is just a noise. But on the other side, this xt minus 1 unknown that we got from this distribution, and by using our diffusion model, it is better because our diffusion model will try to harmonize this region with the known region that we have in xt variable. So now this xt minus 1 unknown that we got from this distribution and based on our diffusion model, it is better than xt minus 1 unknown that we got from this distribution, and it is better than the unknown region inside xt variable. We will combine them together to get the value of xt minus 1 variable. But here in this xt minus 1 variable, the unknown part, it is better. It is more harmonized with the known region. Here we will check if we did n number of harmonization steps or not. Let's say that the number of harmonization steps equal to 10. So now we didn't complete 10 number of harmonization steps. So we will move here, and we will create this distribution based on the value of xt minus 1 variable, beta t minus 1, epsilon t minus 1 that we will get from the standard Gaussian distribution. This distribution, we will use it to move from xt minus 1 to xt. Now this xt, it is better than the previous xt because here the unknown region is more harmonized with the known region, like what we said previously. We will pass this xt through our U network, and here we will not change the time step that we are in right now. We will stay on the same time step until finishing 10 number of harmonization steps. So we will pass the same time step again through our U network. We will compute the predicted epsilon. We will generate the distribution that we will use to get the value of xt minus 1 variable. We will take just the unknown part of xt minus 1 variable, which is better than the previous xt minus 1 unknown part, because it is now more harmonized, because we did 2 harmonization steps now. And we will do the same thing. We will use x0 with mask and epsilon 0 and t minus 1 and alpha bar t minus 1 to generate this distribution that we will use to move from x0 to xt minus 1. We will take just the known part of xt minus 1, okay, and we will combine the known part with the unknown part here, and here we will check if we finished 10 harmonization steps or not. Let's say that the number of harmonization steps is 2. So we will activate this branch, and here what we will do, actually we will take the value of xt minus 1 and we will make xt equal to xt minus 1, and we will reduce the time step by 1. So in other words, it means that we moved 1 time step backward, which is our reverse diffusion process. And they found that it is better to not use Repaint algorithm after each time step, but after a number of time steps. Let's say that after 10 time steps, we will apply this algorithm, this operation, this harmonization process. Let's say that we are at time step 1000, okay? And we will do the normal reverse diffusion. We will move 10 time steps backward, so we will reach 990 time step. And here we will do Repaint algorithm. We will apply 10 harmonization steps during time step 990. And after finishing these harmonization steps, we will move 10 time steps backward, and we will reach 980 time step, and we will apply harmonization steps again to harmonize the unknown part with the known part. So now, why we need to move 10 time steps before applying this operation? Because that they found that by doing this, we will make sure that the semantic information in our unknown part will match the semantic information in our known part in our x0 variable after moving 10,000 time steps backward. Now we will learn how to apply all these things practically. Hi, in this lecture we will learn how to implement Repaint algorithm. Firstly, we will specify the device that we will use, which is our GPU. We will use it to make the inference faster. Or in other words, we will use it to make the reverse diffusion faster. Okay? And here we will install diffusers package, datasets package, and transformers package. Here we will import DDPM pipeline from diffusers package. And here we will create this variable, model ID variable, which represents the path of the model that we want to use. Here, the diffusion model that we want to use. Here we will load pre-trained model. This model, it is able to generate images for bedrooms. The width and height of the images that we will get from this model equal to 256. As you can see here, we will take the path of the model ID from Hugging Face community like this, and As you can see here, this pre-trained diffusion model will generate images for bedrooms. Okay. Now we have the model ID. We will download this model. We will type pipeline object equal to ddpm pipeline dot from pretrained, and here we will pass the model ID. And here we will send our pipeline to our device that we want to use, which is our GPU. By doing this, we will make our model, our diffusion model, inside our GPU, so we can get the results from our U network or our diffusion model faster. And now we can use our pipeline, our diffusion model, to generate the images like this, pipeline.images. And here we will get the image, and we can save it here in this place. Okay. And here we will pass the name of the file that will represent our image. So we will type image.save, and here is the file name of our image, which is clearimage.png. Now we have our clear image. I previously used the diffusion model to generate this image, and I created a mask for this image, which is this one here. Also, we will keep the information in our clear image that corresponds to the white regions in the mask, while we will delete the information in our image that corresponds to the black regions in our mask. Okay. And now we should know that each pixel inside these white regions equal to 255, while each pixel inside these black regions equal to 0. If you want to know how I created this mask, it's easy. Let's say I have this image in my desktop, and now I will create a copy for this image. Let's change the name of this copy like this. I will call it mask. Okay. Now I will open it using Paint program. I will zoom in like this. And now what I will do, I will make the regions that I want to keep. I will make them white regions. So how can I do that? I will click on this place here. Let's say that I want to keep this window as it is. So I will click here and drag this, and that's it. Now I will click on delete. So now this place, it is white, which means we will keep this part of this image. Let's say that we want to keep this thing also. We will do the same thing. We will click here, and we will surround this area here, and we will click here and select delete. So now we will keep this region also because it is white. Let's say that we want to keep this region also, so we will click here and we will surround this region. After that, we will click here, right click, and we will click on delete like this. It is white region, so we will keep it also. Now we will mask the regions that we want to change in our image. So like this region, we don't want this region. Okay, how can we do that? How can we replace this region with black? It's easy. We just need to click here and we will select black like this. Now we will click on delete. Okay, so now we mask this region, or we removed this region. Our diffusion model will try to complete this region with something new. We will do the same thing here. We don't want all these things here, so we will click on delete like this, and the same thing here, delete, and the same thing here. We will mask this region also like this, and we will mask this region also like this. Okay, now we have our mask. We also need to remove this part here. Okay, that's it. We will save this new image, this mask. We will click on Control S like this. So now we have our mask. We can put it here and we can use it in our code like this. Okay, so now we have our mask and we have our clear image. So now what we should do here, let's go ahead and see. As we said previously, we have two images. Our clear image, which is this. We will load this clear image. How can we do that? Firstly, we will import CV2, OpenCV library, and we will import transformers from Torch Vision, and we will import PyTorch and NumPy as MP, and we will import TQDM notebook as TQDM from TQDM. Okay, now we will download our image from here. So we should copy the path like this. We should click on these points here, and we should click on copy path like this, and we should put it here in this place like this. Okay, and here we should use image read method from CV2 to read this image, and between these two parentheses we will put the path of our image. So now we have our clear image. We will change the order of the color channels from BGR to RGB. We will use this method CVT color from CV2 library, and here we will pass our image, and here we should pass the old order and the new order of the color channels, which is CV2.color BGR to RGB. Now we have our image, and now we will load the mask. So we will use CV2.imageRead, and here we will pass the path of the mask like this. We will click here and we will click on copy path, and we will put it here between these two parentheses like this, and here we will get the mask, and we can also change the order of the color channels. Now what we will do, we will normalize our image. Our diffusion model, our U network, our pre-trained diffusion model expects that the input image to it should be between -1 and 1. The values of the pixels inside our input image should be between -1 and 1. So firstly, we will divide our image by 255, which means that the highest value that our image can take, it is 1, because as you know, the highest value for any pixel, it is 255. So the highest value now equal to 1 after dividing by 255. So now the values of the pixels inside our image between 0 and 1, we will multiply these values by 2. So now the highest possible value for any pixel in our image will be 2. So the values of the pixels now between 0 and 2. We will subtract all these values by 1. Okay? Which means now the range of possible values for each pixel in our image will be between -1 and 1. So the highest possible value for any pixel in our image will be 1, while the lowest possible value for any pixel in our image will be -1. If the value of any pixel previously equal to 0, now it is equal to -1. While if the value of any pixel, if it is previously equal to 255, now it is equal to 1. So now we have our normalized image, which is NumPy array. We will convert it into PyTorch tensor using this method, torch.tensor, and here we will pass our image and we will pass the data type of this tensor, which is float32. As you know, the values here of the pixels between -1 and 1, which means that the values of the pixels are fraction numbers. And we can use this data type float32 for these numbers. Now we will change the order of the dimensions. As you know, the first dimension in our image, it is the height dimension, and the second dimension, it is the width dimension, and the last dimension will be the color dimension. We will make the last dimension, the color dimension, we will make it at the first, and we will make the height dimension after the color dimension, and finally we will put the width dimension. And we can do that using this method, permute method. Now, as you know, our U network expects that the input to it is just a batch of samples. So here we need to add the dimension that represents the batch size. How can we do that? Image.unsqueeze, and here we will put the place that we want to add this dimension in, which is 0. So now we can say that we have the following. So now our image has the following dimensions. Firstly, the batch dimension. After that, we have the color dimension like this. And after that, we have the height dimension. And finally, we have the width dimension like this. This batch dimension, it is equal to 1. By using unsqueeze method, we will add a new dimension with length 1. This new dimension, it is this batch dimension, and the length of it is 1. And we put this dimension here because we put it 0 in this place here. And our U network expects that the first dimension, it is the batch dimension. While previously, the order of the channels was the following: the color dimension, height, and width. And before that, the order of the dimensions was as the following: height dimension, width dimension like this, and finally color dimension. Okay, so now we will send our batch or our image. It is just a batch with one sample, one image. We will send it to our CUDA, our GPU. Now we will work on the mask. Okay, now as you know, the pixels that represent the white regions equal to 255. while the pixels that represent the black regions equal to 0. So now we will make the pixels that represent the white region equal to 1. So we will divide our mask by 255. So now the white pixels equal to 1 while the black pixels equal to 0. We don't need to put the values of the pixels between -1 and 1 here. That's what we should do with the mask. We just need to make the pixels that represent the white region equal to 1 and the pixels that represent the black region equal to 0. And we will also create PyTorch tensor from this NumPy array by doing this torch.tensor, and here we will pass the mask and the data type of the tensor that we want to create, and here we will change the order of the dimensions. We will put the color dimension at the first, after that we will put the height, and finally we will put the width. Okay, and here we will add the batch dimension at the first. And now we have our mask. We will send it to our CODA, our GPU. Here, what we will do, we will multiply our image, our clear image, with the mask, and we will get x0 with mask, like what we said previously in the previous lecture. Now we have x0 with mask. Now what we will do, we will create these variables. The first variable is harmonize steps, which is equal to 10, which means at any specific time step, we will do 10 harmonization steps. And here we have this variable, semantic steps variable, which is equal to 10, which means that we should move 10 time steps before doing repaint algorithm. And here we will get the scheduler from our pipeline. So we will type pipeline.scheduler, and here we have our scheduler. Here we will create a noise. We will type torch.random, and here we will pass the shape of x0 with mask to this method to make the shape of the noise that we want to create, same as the shape of our masked image. And we will send this noise to our GPU, okay, which is the same device that our x0 with mask it is available in. And this noise, it is just the epsilon that we can get from the standard Gaussian distribution. Now what we will do, we will create this loop. So we will type for I in TQDM. This TQDM will make us able to track the progress of the generation of our image. And here we will type range, and inside the range we will take the length of the scheduler.timesteps. Here we will get the number of time steps, okay, that we will do in reverse diffusion. And here we will convert this number into a list from 0 to the total number of time steps. We will pass it through each element in this list. Okay, so now at each repetition of this loop, we will get the time step that we are in right now. So T, which is the time step, the current time step, it is equal to scheduler.time steps, and here we will pass the index of the time step that we are in right now, which is this I here. Now we will check if it is the first iteration of this loop. If I equal to 0, it means it is the first iteration of this loop, which means we are at time step T capital, the first time step in reverse diffusion. Here we will make this xt equal to the noise that we created here, okay? As you know, we will start with noise, with a pure noise, with Gaussian noise. We will make xt equal to a Gaussian noise. that we took from the standard Gaussian distribution. Now we will create another noise, and here what we will do, we will create xt minus 1 with mask. We talked about this thing previously. How can we get this thing, this tensor? It is equal to scheduler.add noise, and here we will pass x0 with mask, and we will pass the noise, this one here, and we will pass time step t minus 1. So now we have xt minus 1 with mask. We will take just the known region from this xt minus 1 with mask, as we said in the previous lecture. Now what we will do, we will create this condition. We will check if we finished 10 time steps or not. We will use modular operation to do that. So we will type I modular semantic steps equal to 0. If it is the case, if we moved 10 time steps backward, at this case we can do harmonization steps. So all these 10 time steps, all these previous 10 time steps are for semantic matching between the known and unknown part. And now after completing these time steps, we will do our harmonization steps at the last time step that we reached. We will do this thing after finishing each 10 time steps. Now we will create this for loop. We will use it to do the harmonization steps. So we will type for h in range, and we will pass the number of harmonization steps to it. So if the number of harmonization steps equal to 10, at this case we will get this list from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we will pass it through each element in this list. And we will do the following. Firstly, we will type with torch.no gradient. Here we don't want to compute the gradients because, as you know, we don't need to train our U network here. We just need our U network to generate the images. We don't need our neural network to update its weights. Okay, so firstly we will prepare the input to our U network. How can we do that? We will type xt model input equal to scheduler.scale model input, and here we will pass xt and the current time step. So now we have xt model input that we can pass it through our U network. So now let's pass it through our U network. So noise prediction or predicted epsilon is equal to pipeline.unit, and here we will pass xt model input and the current time step, and we will get the predicted epsilon. We will use it to get the predicted xt minus 1. Okay, so predicted xt minus 1 is equal to scheduler.step, and here we will pass noise prediction, the current time step, and xt, which is this one here, dot previous sample. And here by doing this we will generate a Gaussian distribution based on these things, and we will take the value of xt minus 1 from that distribution, which is a predicted xt minus 1. And as we said in the previous lecture, we will take just the unknown part from this tensor, and we will combine it with the known parts of this tensor. And that's what we will do here. Xt minus 1, it is equal to predicted xt minus 1 times 1 minus the mask plus xt minus 1 with mask times mask. So what we are trying to do here, 1 minus mask, it means that we will make the pixels that represents the black regions equal to 1, while the pixels that represents the white regions equal to 0, which means that we will mask the pixels of the known region, while we will keep the information about the pixels of the unknown region. Okay, and here what we will do, we will mask, or we will remove the information of the unknown region inside this xt minus 1 with mask, while we will keep the information of the pixels of the known regions. So we will make this thing here, we will make it fill the unknown region in this thing here, and we will get this xt minus 1. Now what we will do, we will create a noise from the standard Gaussian distribution like what we learned previously. And here we will create a noise from the standard Gaussian distribution, and we will send it to our device. And here we will check if we completed the 10 harmonization steps or not. If we didn't finish 10 harmonization steps, so at this case, we will use this xt minus 1 to create this Gaussian distribution. And based on what we learned in the math behind the diffusion models, we can move from xt minus 1 to xt by doing the following: xt minus 1 times the square root of 1 minus beta t minus 1 plus the square root of beta t minus 1 times the noise, which is the previous equation that we used to move from xt minus 1 to xt. But if we completed 10 harmonization steps, at this case we will make xt equal to xt minus 1. So now let's say that we didn't finish 10 time steps. So at this case we are in the semantic steps. So what we will do here, firstly we will prepare xt to pass it through our U network. So xt model input equal to scheduler.scale model input, and here we will pass xt and the current time step. This time step now, it is semantic step, and all the time steps that we need to complete 10 time steps, we will call them semantic steps. And when we complete 10 time steps, we will do our repaint algorithm inside the last time step that we reached. Here we will use our U network noise prediction, or predicted epsilon is equal to pipeline.U network. Here we will pass xt model input, and here we will pass the current time step, and we will get predicted epsilon. Okay, now we will get xt minus 1 using the predicted epsilon, the current time step, and xt. So we will type xt minus 1 is equal to scheduler.step, and here we will pass noise prediction, the current time step, xt dot previous sample, and here we will make xt equal to xt minus 1. As you can see here, these semantic steps, they are just a regular reverse diffusion process. That's it. That is our repaint algorithm, like what we said in the previous lecture. Now let's see the results. Firstly, let's display our original clear image, which is this. As you can see here, I generated many images to fill the mask region. So as you can see here, our diffusion model kept the window as it is, like this, because here our mask here it is white in this region, which represents our window, and our diffusion model, and using our Repaint algorithm, changed the bed. As you can see here, it is different because it is available in this black region in our mask. So now it is different. And our diffusion model kept this place here because it is white in our mask. Now let's see another results, and you can see our diffusion model changed the pad many times. Here is another version, and here is another version here, but all these images have the same window, and as you can see here, and here is another version for the bed. Now as you can see here, we could fill the mask region using our diffusion model, and you can use the same algorithm to work with many different pre-trained diffusion models. Thanks for watching. Hi, in this lecture we will learn how to speed up our diffusion model. The diffusion model that we used previously, we call it DDPM diffusion model. In that model, we needed to move 1000 time steps backward to generate new image, which means that we needed to use our diffusion model 1000 times. At each time, we will move just one time step backward, and that's because the Markov chain. As you can see here, the distribution of x2 variable will just depend on the value of x3 variable, and the distribution of x1 variable will just depend on the value of x2 variable, and of course the distribution of x0 variable will just depend on the value of x1 variable. So we should move from x3 to x2, and from x2 to x1, and from x1 to x0. And that's not good, because if the number of time steps that we need to generate any image is large, let's say 4000, in this case we will take long time to generate any image. In other words, we will use our diffusion model 4000 times to generate any image. In this example, we need to use our diffusion model 3 times. Here to move from x3 to x2, and here to move from x2 to x1, and here to move from x1 to x0. So now how can we break this Markov chain? We will do that by using our reparameterization trick. Previously we said that our loss function, it is just the difference between the target noise, the actual noise that we added to our clear image, and the predicted noise that we will get from our U network after passing xt variable and the current time step. And based on the reparameterization trick, we can say that xt, it is just the square root of alpha bar t times x0 plus the square root of 1 minus alpha bar t times epsilon, which is just a noise from the standard Gaussian distribution. And here we will also pass the current time step. Okay. So now we have xt and we have the predicted noise. And based on the reparameterization trick, we can also move from xt to x0 directly. How can we do that? The predicted x0, it is equal to 1 divided by the square root of alpha bar t times xt minus the square root of 1 minus alpha bar t times the predicted noise after passing the value of xt variable and the current time step to our new network. This formula, it is just the formula that we got after applying the reparameterization trick. But here we want to find x0, not xt. So let's say that we are at time step 3 here in this place, and we want to move directly to x0 like this. We can do that using this formula here. But of course, this x0, the predicted x0, will not be good, where we need to move many time steps to make the predicted x0 gets better and better. But the idea here is that we can jump from any time step to x0 directly using this reparameterization trick. So based on what we said, we broke the Markov chain here. We jumped directly from x3 to x0. And because that we will not get good quality image if we jump directly, let's say, from x3 to x0. So we will not jump directly from, let's say, the first time step to the final time step t capital to time step 0. But we will use this property to reduce the number of time steps that we need to move from time step t capital to time step 0. How can we do that? The idea is easy. Based on the formula that we got after applying reparameterization trick, xt equal to the square root of alpha bar t times x0 plus the square root of 1 minus alpha bar t times epsilon t. Epsilon here, it is just a noise that we will get from the standard Gaussian distribution. Epsilon t, it is same as epsilon t minus 1 and epsilon t minus 2 to epsilon 0. And based on this formula, we can say also that xt minus 1 it is equal to the square root of alpha bar t minus 1 times x0 plus the square root of 1 minus alpha bar t minus 1 times epsilon. By using this formula, we can jump directly from x0 to xt minus 1. And you should know that we can find the predicted x0 at any time step. So now, let's substitute the value of the predicted x0 here, this place, and we will get the following, this formula here. Xt minus 1 will be equal to the square root of alpha bar t minus 1 times xt minus the square root of 1 minus alpha bar t times the predicted epsilon, like this, divided by the square root of alpha bar t, which is this thing here. So now we can find the value of the predicted x0 just by knowing the value of xt variable and the predicted noise at time step t, plus this thing here, which is the square root of 1 minus alpha bar t minus 1 times the predicted epsilon. Here we will not take the epsilon from the standard Gaussian distribution to move from x0 to xt minus 1, but we will use our U network to find the predicted epsilon that we can use to move from x0 to xt minus 1. And now we can say that this xt minus 1 variable, it is not a distribution. It is just specific value that will depend on our U network, the predicted noise from our U network. By using this formula, we will get the value of xt minus 1 variable. This thing here, it is the predicted x0. And here it's like that we are trying to move from the predicted x0 to any time step. In this case, time step t minus 1. So let's say that we have 4 time steps. Let's call this one the predicted x0. Okay, now here we have x1, x2, x3. What we want actually, we want to make this reverse diffusion process faster. We want to reach the clear image faster with a few number of time steps. How can we do that? Let's say that we are at time step 3. What we will do based on this formula, we will jump directly to the predicted x0 based on this formula here. So now we are at time step 0, and now we have this predicted x0. It is not good because we need to move few time steps to make it better, but now we are at time step t0. What we will do here, we will add a noise to move us from this predicted x0 to any time step. At this case, we need to jump this time step 2. So we will add the noise to move us to x1 like this. So we will use our U network to find the noise that will make us move from the predicted x0 to x1. But now you might ask yourself, this noise, it is just will make us move from xt to xt minus 1. But actually, based on the reparameterization trick, we just add a noise to the clear image like this, and it means noise, and we scaled them by specific amount. Let's say 1 minus alpha bar t, and this one here alpha bar t. So here we are trying to find this noise, and we can scale it as we want to move it to any time step. Here in this case, time step t minus 1. But we can make it t minus 10, t minus 30, and something like that. As you know, we need to jump a few time steps to make the generation process faster or the reverse diffusion process faster. So now we will move from the predicted x0 to x1. So we jumped this time step, and we can actually jump more than one time step, like 30 time steps, or actually we can generate good images with just 50 time steps. For example, let's say that we will start with time step 1000. We will jump 20 time steps, and we will reach time step 980. We will jump 20 time steps again, and we will reach time step 960. By doing this, we will just need 50 time steps to move from time step 1000 to time step 0. While in DDPM we need to move 1000 time steps, but here we can move just 50 time steps to generate the same images. Now we are at time step 1. We can also do the reverse diffusion to move to x0 like this. So now this predicted x0, it is better than the predicted x0, the previous predicted x0, because this predicted x0 generated from 2 time steps. If we want to mix between the DDIM and DDPM, we can add a noise from the standard Gaussian distribution. We will add this standard deviation and this here to make it DDPM and DDIM at the same time. But here in DDIM, the most important thing here, we will not add a noise, so the generation process it is deterministic. Which means if you start with the specific noise, okay, and do the reverse diffusion with the DDIM model, you will get, of course, an image. And when you use the same noise and do the reverse diffusion again, using our DDIM model, we will get the same image. We will not get another image, because here the generation process it is deterministic. But it's not the case with this thing here, with this formula here, because here we are trying to mix between DDPM and DDIM, so we will get many different images for the same noise. Thanks for watching.